Om Nam Shivaya. Good morning, all. Hope you are all safe and doing very well. We are all here today for in fact, the first online symposium on multifacets of chemistry research. So this is organized by Department of Chemistry, Amrita Vishwavidyapeetham. So actually, as the name itself says, we have four speakers today coming from four different areas of chemistry research, giving us a glimpse of what research they are doing. I think this will be very useful for our students and even for us to know what others are doing, how the research is actually going all around the world. Okay. So we have Professor Sakthivel from Central University of Kerala giving his talk. And then we have Dr. Sharma from University of California, Riverside. We have Dr. Lenin from Central University of Gujarat. He's basically an organic chemist. Sakthivel, is a material chemist. We have Sharma, is a theoretician. And then we have Dr. Animesh Das from IIT Guwahati, who is an organometallic chemist. I hope so. This will be this whole event would be enjoyable. I hope the students will make the good use of it. So we have today with us our beloved principal, Nandakumaran sir. We have our HOD, Professor Mangalam, and then we have Professor Padmanabhan sir, and then all the faculty of chemistry department online. And we have, I could see, about 60 plus students from INT MSc and MSc division. So, and then I see that many of our guests are also online. So I think we can start the program now. So I think we'll start the program with the prayer as we always do. So I request Mr. Krishnan Unni to sing the invocation.
Namaste. ध्यायामो धवलावगुण्डनवतीं तेजोमयीं नैष्ठिकीं स्निग्धापाङ्गविलोकिनीं भगवतीं मन्दस्मितश्रीमुखीं वात्सल्यामृतवर्षिणीं सुमधुरं सङ्कीर्तनालापिनीं श्यामाङ्गीं मधुसिग्धसूक्तिम् अमृतानन्दात्मिकाम् ईश्वरीम् माणिक्यवीणाम् उपलाळयन्तीम् मदालसाम् मञ्जुळवाग्विलासाम् माहेन्द्रनीलद्युदि कोमलाङ्गी मातङ्गकन्याम् मनसा स्मरामि.
Thank you, Krishnanuni. Now I request our HOD, Dr. Mangalam, to welcome the gathering. Ma'am, we can't hear you.
She has to unmute it. I think she has not unmuted.
Yeah.
Okay.
Yes. So thank you, Naveen. Good morning, everybody. Om Amriteshware Namaha. My humble pranams at the lotus feet of Amma, Mata Amritanandamayi Devi. We seek her blessings for our first symposium to go on well. I think I'll close the video because it is giving some sort of disturbance, I think.
No, it's not your video. I think the others will have to mute their audio.
Huh. Respected speakers for today's symposium, Principal Dr. Nandakumaran, my colleagues, students, and all others who may be attending from different parts of the country and globe. It is indeed a pleasure to welcome all the four speakers for today's symposium: Professor A. Sakthivel, Dr. Sharma, SRKC, Yamijala, Dr. Dandamudi V. Lenin, and Dr. Animesh Das, who will be enriching our knowledge in their respective areas of research. A warm welcome to all the four speakers. A warm welcome to our dear principal, who has agreed to be a part of the symposium to felicitate the function in spite of his busy schedule. To all my committed colleagues and to all our dear students for this symposium. Research in chemistry is advancing by leaps and bounds, and therefore it becomes important for us to keep abreast of the latest developments in the field. And that is where a symposium becomes important in our curriculum. Every growing institution needs to conduct workshops, symposia, and conferences periodically. In the present scenario, where it is not possible to have these physically conducted for obvious reasons, we have chosen to conduct an online symposium. This is the first one from our department, and we intend making this a regular feature in the days to come. These kinds of activities will be very beneficial for a larger section of students from all over the globe. Online activities are thus much more far reaching. Next time, probably, we will issue e-certificates for participation for all those who participate in the entire function. Now let us get on the rest of the program. I once again extend a very warm welcome to one and all for this first symposium, Multifacets of Chemistry Research, conducted by Chemistry Department, Amrita School of Arts and Sciences, Amrita Vishwavidyapeetham. Dear students, stay tuned for all the four lectures. Thank you.
Thank you very much, ma'am. Now I request our beloved principal, Professor Nandakumaran sir, to speak few words.
Okay, thank you, Naveen. Respected speakers, Dr. Mangalam, Dr. Padmanabhan, faculty members, and my dear students. I'm extremely happy that the Department of Chemistry is organizing this online conference titled Multifacets of Chemistry Research. And I congratulate Dr. Naveen Kulkarni, Dr. Mangalam, and the other faculty members of the department for arranging such a conference during these stressful days. As we know, our lifestyle and our other activities are undergoing fundamental changes. I would say Corona-induced changes. The mode of imparting knowledge itself is changing rapidly. The Kerala government, in fact, has started online classes from standard 1 onwards in Kerala. Therefore, it is only appropriate that we have an online conference today organized by the chemistry department, I believe for the first time in our Amrithabadi campus. Online mode of teaching, I believe, will become more and more common during the post-COVID days, if there is such a thing as post-COVID days, because I am told that we have to probably live with the COVID for the next few years. So this post-COVID days is only a kind of usage. It will be in future more teaching and learning from home. Actually, in this context, I am reminded of a short story by the famous science fiction writer Isaac Asimov. The title of the short story is The Fun They Had. It deals with something in future, and he had put the year as the 2021-55, where the whole teaching will be done by robots. These robots will be planned in such a way that they will teach according to the requirement of the students. So every student will have his own level of understanding or level of capability. So it will be accordingly like that, and not by humans. So by accident, one of the students find a notebook by one of her great grandfathers, and was wondering how they were having their school days. And finally, they find that their great grandfather had a very interesting life. That's what they call the funds they had. Now, thanks to our Corona, such a scenario has come now, 135 years earlier, predicted by Isaac Asimov. But the only thing is we don't have a robots as a teacher. We still have humans. And I believe that maybe after about 20 years, humans also will be replaced. As Padmanabhan was telling, probably initially only few faculty members will be there. And probably after some time, they also will be replaced by robots. I don't know. Anyway, I am digressing. Let me wish all the success to this conference and hope that the participants will have a fruitful time during the next few hours. Thank you.
Thank you very much, sir. Thank you very much. So, now I request Professor M. Padmanabhan to address the gathering.
Hello. Am I audible?
Yes,
okay.
Very clear.
Okay. Professor Nandakumar, Professor Mangalam, Dr. Naveen, Professor Sakthivel, Dr. Sharma, Dr. Dandamudi, Lenin, Dr. Animesh Das, and dear faculty members and dear students, and then other participants in the online symposium. I must say I'm so happy to be part of this online symposium. And I must congratulate and thank Professor Mangalam and also Dr. Naveen. In fact, Naveen did talk to me initially and how he is going to conduct this program. And I know he has taken a lot of pain. Now it looks like it's very, very easy for us, but then I know he has worked very hard for several days and contacted people outside. And we have got 4 speakers who will be talking on, I must say, in fact, 4 different disciplines, different areas of research. Once again, congratulate Dr. Mangalam and also Dr. Naveen for taking the pain and efforts to conduct this symposium. I know all of us are going through a very hard time in our life. As Nandakumar said, actually, we are now living in a situation where we are going to take a different route. I mean, from our conventional teaching and learning. Dr. Nandakumar said actually teachers should be going to be replaced by probably robots. But there's some kind of a doha, I think Hindi doha. You say that Guru Govinda do khade kake lagum pai, Balihari Guru apne Govinda diyo batai. You say that Guru and Govind, teacher and then the God is standing in front of us. And now I have the doubt actually, whom should I pray first? I mean, rather fall on his feet and then seek his blessing. Then Tulasidas says that no hesitation, we should fall on the feet of the Guru, because Guru is a teacher and he is the person who has taught you about the God. So I think the teachers will have their own roles, and we will continue to teach the students and inspire the students. And I'm so happy that Dr. Naveen has arranged this in a short time, and of course Dr. Mangalam too, at least. And regarding the speakers today, I see Professor Sakthivel. Sakthivel, are you there? Can you hear me? Hello.
I'm there.
Thank you. In fact, we know each other for long, and he has been talking to me or briefing me about his work. And he does wonderful chemistry with Prof. He works on other areas too. And I understand the work he's going to share with us today is done by one student, actually, it's Anjali K. I think she's also
Yeah.
part of it, actually. And she's
Yes,
our
sir.
former student, a topper in one of the classes, and whom I have taught for a while at least. In fact, I met her when I visited Central University of Kerala some time back at least. And I'm so glad that actually he's going to share with us actually the work he has been doing on porphyrin, metal porphyrin and chlorodium-based porphyrin, and talking about catalysis he has done with the wonderful catalyst. And Dr. Sharma, of course, he will be talking on different topic, and he's a computational chemist, as I know, worked with the great Sopan Padi, and he works on, I think he's going to talk about maybe CF activation, am I right? Maybe fluorine elimination on polyfluoroalkyl derivatives and converting them into alkenes, actually. I'm so glad actually he has joined us. And of course, time there must be around 9 in the night, actually, if I guess. Am I right, actually, Sharma? Naveen must be right?
Yes, sir. Yes, sir.
Yeah, 9 in the night,
Yes.
actually. We are here on Tuesday and he's there actually. For him, it's only Monday. I'm so happy that he's actually going to share with us the work he has been doing. Actually. And Dandamudi Lenin, actually, he's a hardcore organic chemist. Actually, he'll be sharing with us new methodologies of synthesis of carboxylic heterocyclic molecules. And we are eager to listen to you, Dr. Lenin. And Dr. Animesh Das probably will be talking about two aspects. I think it's one is about, it's a transition, even though Dr. Naveen said he's a organometallic chemistry. I think he's going to talk to us about a metal-free catalysis, if I get it right. Is it true, Naveen? He'll be talking to us about transition metal-free, regioselective cyanation and so on. And we are so eager to listen to you, Dr. Animesh Das. And once again, I thank the Dr. Mangalam and also Dr. Naveen and all the other faculties who has contributed or helped the our head of the department, Dr. Naveen, to organize this one. And also thank all our faculty members who are present today, and also our research scholars and our students, and also a lot of people from, I think, maybe even from Central University of Kerala and other places. So thank you once again, and also thank Dr. Mangalam and also Dr. Naveen for giving me a chance to speak to you for a few minutes. And thank you once again. I wish that all of you, or rather pray that all of you will have a safe time hereafter, and also will enjoy the listening to enjoy, and then we'll listen to talk and enjoy the work people have done, at least in different areas of chemistry. Thank you once again.
Thank you very much, sir. So now I think it's the time to move to our core session. So we'll have our first speaker, Professor Sakthivel from Central University of Kerala. So, sir, if you can please come online.
Some
pitch.
Yeah. Can you see?
Yeah. Yes, sir. Yes, sir. I can see.
Yeah, I'll share the PPT.
Yes, sir. So a brief introduction about Professor Sakthivel. He's currently serving as a professor at Department of Chemistry, School of Physical Science, Central University of Kerala, Kasaragod. So he obtained his MSc from Madurai Kamaraj University in 1997, and he got the PhD from IIT Bombay in 2002. He has many years of postdoctoral experience at various prestigious institutes from Taiwan, Germany, where he was a Humboldt Fellow, and then in Japan, where he worked as a JSPS Fellow. So he also worked as a senior manager, R&D division in Reliance Industries Limited, Baroda. So before joining Central University of Kerala, he actually worked as an assistant professor at Department of Chemistry, Delhi University for about 6 years. So he has plenty of teaching experience and as well as the industrial experience. His primary research interests are basically material chemistry and heterogeneous catalysis. He has about 100 plus publications in international reputed journals and has several book chapters and books to his credit. He's a recipient of several awards and recognitions. So I cannot read the whole list. It's a big list. So to name few, so he was inducted as the Fellow of Royal Society of Chemistry from 2019. So we are very happy to have you, sir. So we'll be eager to listen to your talk. So it's over to you.
Thank you, Naveen. Can you see my slides?
Yes, sir. Yes, sir. Yes, sir. If you can make it full screen.
Yeah, I'll do it. Okay, yeah. Just a minute. Yeah, I think now full screen.
Before I start,
yeah,
I request everybody to mute their microphones and then turn off the videos if possible, so that we can have a clear connectivity and there won't be any issues with the sound and the videos. Okay. Yes, sir. It's so over to you.
Okay, so I'll start. First of all, thank you, Naveen, for I thank Naveen for inviting me to share some of such work. I'm very happy to interact with Amrita, and I'm thank your faculty, all other faculty members, and all staff for inviting me. So here today I'm going to talk about some of the work, as Professor Padmanabhan has said. The work has been done by one of your former students, that is what you call as Anjali. She did this work, so I'm sharing a part of the work which is carried out by the Anjali. So we are sharing. So the work is a heterogenation of rhodium tetraphenyl phosphorine derivatives for the heterogenation catalyst, especially biomass component. Is the work we are going to share. So my talk will be what is first. I'll introduce about what is macromolecules and their macromolecules and their importance. Then I will talk about what is the importance of developing a single site catalyst. When you fix a single component surface, how to make a single site
Professor
homogeneous catalyst, how it is important. I think about the preparation of rhodium containing macromolecule like tetraphenyl phosphorine and tetracarboxyphenyl phosphorine molecules, and then how to organize this and its application for the biomass derivative molecules. Okay, that's what mean by macromolecule. Play.
Professor Sakthivel, I think there is some issues with the your voice. It's breaking, and then we are hearing some continuous background sound. I don't know.
Actually,
yes,
actually, I am sitting outside. Actually, there is no signal in the inside. I tried to connect with my.
Now it is better actually.
Yeah. Okay. There is this microphone. I need to hold it. Okay, I will do it.
Okay,
yeah.
Sir.
Can you? Is it clear now?
Yeah, much better.
Okay. Yeah. Okay. Okay. I will.
The rest should be off the mics.
Yeah, I'm holding it now. Okay. So perforin molecules, you can see that it is present in the all living organism, and it is a 18 electron system having the conjugation by conjugation, and it has a aromaticity, and it is a purple colors, and you can see the nice crystal of perforin which is synthesized in our lab. And the most important thing is we have the two acidic protons which can be replaced with the metal centers. So the metal can be encapsulated in the cavities, and then we can be used for the various catalytic applications. So we can see that there are large number of transition metal ions are incorporated in these kind of molecules and have been utilized for various applications. Here you can see that this kind of perforin molecule has shown a lot of application. And another important macromolecule is a calyx-4 pyrrole. This is actually again derived from the pyrrole unit and the mesoportion having the two dimethyl substitution. And these molecules again have the protons and also have the cavities, which can also drop the transition metal ions and can use as a catalyst. But here the difference between the perforin and the calyx-4 pyrrole is that the calyx-4 pyrrole, the aromaticity is only in the pyrrole center, not in the inside the ring. There is no conjugation in the inside the cavities. There is no conjugation. So that is a basic difference between the perforin and the calyx-4 pyrrole. Once again, the calyx-4 pyrrole also used as a potential catalyst for various applications. Now the challenge is, because we know that often when you do with the homogeneous catalyst, it is very difficult to recover and recycle. And second thing is, these kind of macromolecules under the atmospheric condition, it can go for polymerize, and then it is very difficult to stabilize. So these are the two major problems. So how we can overcome? It's the same type, similar to how the biological molecules are anchor in biologically, perforins are anchor on the globin center. Same if you fixed fence moiety kind of you can generate in the surface like silica or alumina or molecular sieve will be interesting. So among the molecular sieve, you can see that the molecular sieve materials can be classified into three categories. That is microporous, mesoporous, and macroporous. So among the molecular sieve, this mesoporous has got a great interest because this mesoporous molecule have the lot of surface selenol group. You can see that there are a lot of surface selenol group. You can see that, and this selenol group will be useful for anchoring the organometallic complexes as well as many other applications. Besides, this microporous molecule, this mesoporous material have the pore size of 6 nanometers. So when the pore size is 6 or more than 6 nanometers, there is no diffusion limitation of the molecules. So that also makes this mesoporous material is quite interesting. Here is some of the example I have shared with you. For example, the molybdenum oxo complexes, then cerium based complexes, even the cobalt carbonate complexes, they are all shown as a epoxidation, hydroformylation, those kind of reaction using this material has been shown. So in these kind of materials are found interesting for the fixing these macromolecules. So our aim is to fix this macromolecule on the mesoporous material and then explore its application for the hydrogenation of biomass relevant compound, so that we can convert the biomass into valuable chemicals. That I will discuss in the later. Okay. So overall objective is to prepare in particularly rhodium containing tetraphenyl perforin and then tetracarboxyl phenyl perforin and rhodium CP calyx-4 pyrrole molecules we plan to prepare, and then those molecules has been crafted on the surface to get a single site catalyst through the axial position of the perforin, that is metal axial position. So through the amino silane linker which is present in the mesoporous molecules, and then these materials has been studied for the various applications like hydrogenation, nitroarine, and the biomass derivative molecules. Okay. So before going to that, we also talk about what is the importance of rhodium. Everybody knows that rhodium is one of the best what we call as a hydrogenation catalyst. So the best example is the Wilkinson catalyst, which is known as a potential catalyst for the hydrogenation of variety of functional groups. You can hydrogenate any kind of functional group present in the organic activity. The interesting aspect is we often use the phosphine-based ligand has been used in the catalyst. So here our interest is to prepare the phosphine-free Wilkinson type, that is a rhodium-based catalyst, that is macromolecule catalyst, and then encapsulation on the heterogeneous surface and explore for its activity. So in this aspect, we synthesize this rhodium-based porphyrin complex. All the synthesis has been carried out in the slump line, and the reaction has been studied in the high pressure reactor, where we can go up to 100 bar. So here the general synthesis scheme. So we take the benzaldehyde and the pyrrole for the tetraphenyl porphyrin synthesis. In presence of propionic acid, then when you reflux it, you will get a purple crystals. Then after washing thoroughly with the solvent and purifying, we got a purple crystals. Then in which we introduce the metal salt, mostly rhodium chloride. When we introduce, then we after rhodium salt in the solvent, when you reflux it, and then followed by pentane washing, we could be able to get a clean material of rhodium TPP complex. Same way, in the case of tetracarboxyl phenyl porphyrin synthesis, instead of benzaldehyde, we have been used as a 4-formyl benzoic acid as a what is called as a electrophile. We are used as electrophile and pyrrole as a nucleophile. In presence of again the propionic acid, we could able to get a TCPP, and then which is further treatment of metal salt in presence of solvent like acetone, then we could able to get a metal complexes. So then first thing is how we are going to confirm the formation of the this tetraphenyl porphyrin and a rhodium tetraphenyl porphyrin. We can see that the first thing is proton NMR we have carried out. So we have the mesocarbons, that is a mesocarbon we have, and then we have the phenyl and pyrrole. So in the proton NMR, you can see that there is a protons A. The A proton is corresponding to the what is called the NH proton. So which is normally occur at a upfilled, highly shielded regions, that is minus 2.74. So once you introduce the metal ions, you can see that the absence of this signal, absence of peak correspond to A, that is a minus 2.27, which supports that the proton in the chiral unit is going to coordinate with the metal centers. Again, the formation of TPP and rhodium TPP confirmed with the mass spectral analysis. Same way, the case of rhodium TCCP, again the NH proton in the TCPP is occur around minus 2.7, and which is disappear once there is a rhodium TCPP has been introduced. So in the it shows support that rhodium is present encapsulated, or it is coordinated in the cavities of the macromolecules, and then the formation of the rhodium TCPP again confirmed with the mass spectra, where there is a mass is well matched with the theoretical value. Then we also prepared the rhodium CP molecules. So pyrrole, then here is the electrophile is acetone. So in presence of just at 0 degrees centigrade, when you treat with the in presence of propionic acid, again we can get a pyrrole, calyxpore pyrrole. It's a ivory color. Then once washed thoroughly, then it's subsequently metal chloride in presence of acetone. Then we could be able to see the metal of calyxpore pyrrole, that is rhodium CP. We could be able to see that. So once again, the formation of CP and rhodium CP can be confirmed through the what is called as a proton NMRs. Here, the NH proton of the CP comes around a de-shielded region, that is 7.1, whereas when you reduce the rhodium, the absence of your NH proton support that there is a rhodium ions is encapsulated in the incorporated into the macromolecules. Then we also studied with the UV spectra. So UV spectra, you can see that tetraphenyl porphyrin shows that there is a Sorad bond which is around 405, and then Q bond, there is a quadrat, there is a Q bond which is also appear. But then after the metal incorporation, we can see that the improvement of symmetry of this complex, that is metallocycles, will lead to the number of Q bonds going to decreases, because this energy gap between these going to be reduces. So that's why you will see that the reduction of the Q bond, we can normally see that. And also we can see that the red shift towards what we call as a presence of metal support the red shift in the UV spectrum. Similar observation also seen in the calyxpore pyrrole, where there is the initial, it shows the 204 for the what we called as a your metal complex, and then your calyxpore pyrrole, when the metal incorporation there is a red shift we can see in this calyxpore pyrrole, rhodium burning calyxpore pyrrole also. Then another important aspects, the NMR, that FTIR also of these complexes also show that this NH and CH2 protons vibration corresponding to the tetraphenyl porphyrin Whereas when there is a rhodium is incorporation, you can see that there is a vibrational band at 672 nanometer, which is corresponding to metal nitrogen bond. That is a rhodium nitrogen bond is that. So first we have prepared completely rhodium TPP, rhodium TCPP, and rhodium CP and thoroughly characterized. Then the next part we prepare the heterogeneous catalyst. First we prepare heterogeneous support and then encapsulate. So to prepare the heterogeneous supports, we use the P123 polymer as a surfactants in presence of HCl, tetraethyl orthosilicate as a silica source. Then when you stir under that acidic medium, you will get a silica gel. The formation of polymer as a micelle, which will convert it into hexagonal array and form the mesoporous hexagonal SDA15 material will get. So once you calcine this material, what you will have is you will have the surface hydroxyl group. It is like a wall in which you have the surface hydroxyl group is there. So this surface hydroxyl group, when you treat with some kind of siloxane, this is called siloxane, methoxysilate, this methoxy and hydroxyl group can easily react and forming a linker. It is called as the amino functional group is a linker. It can be diamine or it can be monoamine, amino functionalized. Siloxane can act as linker, and you will generate what is called the surface functionalized SBA15 materials. So where surface having NH2. So this has been confirmed with what you can see from the IR. There is a NH2 vibrational band. We can see that, and also there is a shift in the functionalized material. We have the XRD. We see the mesoporous material, which we normally observe the 0.85 as a 2 theta value. The first peak, that is an external characteristic peak observed at 0.85. Once you introduce some bulk molecules inside, the 2 theta value shifting to the higher angle. That means your pore size is reduced. That is because of the introduction of amine functionality inside the channels. The presence of, then we subsequently what we did, the treatment of this amino functionalized group with the rhodium macromolecule, that is rhodium TPP or rhodium TCPP or what is called as rhodium CP. When you have the axial portion of the macromolecule is going to be coordinated with the NH2 and then have the strong binding with the materials. So the coordination of rhodium nitrogen bond present in the heterogeneous support also we can see from the observed metal nitrogen bond in the FTR spectra. Another important factor, we can confirm the presence of macromolecules inside the channel of the mesoporous by a simple what we call as a nitrogen sorption method. So normally you can see that this is SBA15 material where the A sample, where you can see that there is a type 4 isotherm that is in the P by P0 region. There is a 0.8. You can see that there is a sharp take. There is because of the capillary condensation. So the capillary condensation of nitrogen inside the uniform mesoporous channels will give the type 4 isotherm. What will happen when you introduce a functional group? There is a drastic reduction of the what we call as a nitrogen volume is going to be reduced drastically. Then subsequently, when you introduce rhodium CPP and rhodium TPP or macromolecules, when you introduce, you can see that the surface area is reduced drastically, and then there is no pore volume. There is a absorption is also drastically decreased. What does it mean is the volume that macromolecule is successfully inside the channel of the or cavities of the what we call as a macromolecules. This can be, you can see from the BET data and the BJH pore volume, but then you can see that the pore size is still accessible. The macromolecule is there inside, but still we can access the pore. That's what indicate from the last column. Then the proton and the C13 NMR of the heterogeneous catalyst support that the presence of what we call as a linker. You can see that the peak appear at hello, yeah, hello. So the C13 NMR also support that the presence of what it calls a TPP molecules after heterogenation, it is really intact. So here, then what we did is we first studied its catalytic behavior for the what is called a nitroarene reaction, because nitroarene is the easiest one which can be reduced under the hydrogen, in presence of hydrogen. So when you do that, this molecule has been efficiently hydrogenate all the nitrofunctional group, irrespective of the whether electron donor or electron withdrawing group present in the functional group. So based on that interest, then we subsequently move on to the what is called as one of the important biomass component, that is levulinic acid into gamma varroa electrons conversion, because the gamma electron is used as a additive in the fuel, which is useful for the value added chemical for the conversion of biomass into value added chemical. So that's what we have done in this work. So the formation of the lactone can be seen that new peak IR peak around 1721, that we can see that. Then rest of the things we have analyzed with the GC and the GCMS. We have product has been confirmed the GCMS, and yield and conversion has been calculated with the help of the what is called as GC. So here you can see that first we are studied with a different solvent like IP, that is isopropanol, dimethyl formamide, butanol, and water. You can see that in all the cases, among the things, IP shows that exclusively formation of what you call as your complete conversion of levulinic acid with a gamma-orololactone. GVL is a gamma-orololactone. There is alignment problem, but it's a here 100% gamma-orololactone has been applied. Whereas when you use the water, you can see that there is a formation of diol as the major product. So because of the gamma-orololactone can be further converted into diol in presence of water. That is the reason we got presence of water. Use the diol as the conversion. And then we can study it with a different hydrogen pressure. So we can see that when the hydrogen pressure is increases, basically you are doing all the reaction has been carried out 100 ml autoclaves. As the hydrogen pressure is increases, you are going to increase the number of moles of hydrogen is also increases. That's why when you reach this 100 ml, that is 10 bar, then you can reach the hydrogen substrate to hydrogen ratio will be 1:5. So which facilitates the complete conversion with the gamma-orololactone as a major product. The same way with respect to temperature also. As the temperature increases, at the temperature around 100, you will get a complete conversion of levulinic acid with the formation of gamma-orololactone has been applied. Now we have compared with the TPP and TCPP, that is a homogeneous catalyst. Then there is a heterogeneous catalyst, rhodium TPP SPA and rhodium TCPP SPA. So the interesting thing is you can see that when you do the homogeneous catalyst, as the number of cycle goes, you can keep on decreasing the conversion. You can see that. But then all the cases, gamma-orololactone is the major product. Whereas if you use the rhodium TCPP, you will get a diol as the major product. But the conversion is stable, but then you will get a more of diol as a major product, because the high polarity of TCPP facilitate the water formed as a byproduct which interact with your gamma-orololactones and give the diol as a major product. Whereas in the case of rhodium TPP on heterogeneous surface, when you take a support, you will get the conversion is remain stable even after 4 cycles. Another important thing is that the gamma-orololactone selectivity is improved at the process of many cycles, which may be due to that the water formed may be absorbed on the support, which protect your catalyst and facilitate the better selectivity. There is a exclusive formation of gamma-orololactone in the case of heterogeneous supports. Based on that, we have proposed the mechanism. The reaction has been facilitated with the removal of axial bond, one of the axial bond where we have the hydrogen halide or any other water molecule will be there. So once you remove the axial bond, then another axial position, there will be a coordination of levulinic acid either to the carboxylate ketone, carboxylate double bond O, C double bond O, or keto double bond O. So through the carboxylate double bond O, you will get a 1,4-pentane diol as a major product. Through the keto group, you will get a gamma-orololactone as a major product. So this is based on the reaction path is depends upon the pressure which lead to the different product we can see in the based on data. So then subsequently we also studied this molecule for the various substrate. In mostly the olefin can be completely converted, whereas other like functionality like furfural and other things will give you the comparable conversion you can see in the both heterogeneous and homogeneous catalyst. So we have demonstrated that how to prepare the single site catalyst by the using the support like functionalized SBA15 support on by taking macromolecules. So these kind of macromolecules can be used for various other biomass components. We are working on different types of biomass component conversion. And another important aspect also we are working with how to utilize the CO2, that is CO2 to methanol, CO2 to cyclic carbonate, those things also, these kind of macromolecules can be used. These are the future scope of this work. So we demonstrated the preparation of metal macromolecules like metal containing tetraphenyl porphyrin, metal containing tetracarboxyphenyl porphyrin and alexporpyrrole and hydrogenase, and then explore its application for the hydrogenation of levulinic acid. And then finally, I like to thank my students. So this Anjali, you can see here, she's the one who did all the work. She works. There is no Saturday or Sunday. All the days she comes and works. Just now she completed her free synopsis. She will soon submitting thesis. And this work has been published in New Journal of Chemistry and Tolerant Construction. So these are some of my former students and collaborators. I thank all of you, and I thank organizing committee also for inviting me to come and share some of my work. Thank you for listening me. Okay, if you have any question, I am happy to answer.
Thank you much for taking us through the wonderful journey of this buffer in chemistry. It's so interesting.
Yeah.
I think we have time for maybe a couple of questions.
Dr. Naveen, I have a few questions.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Am I audible?
Yes, sir.
Yeah, okay.
Yes, sir. Yes,
Yeah,
sir.
audible. You're audible.
Yeah, Dr. Sakthivel, great work, I should say. And of course, you had briefed me some time back about your work a little bit. I have a few questions. One is regarding your purification of a TCP. How did you do it? Because TPP is not an issue because TCP has got a COH functional group and a column chromatograph gets stuck on it. And I'm just curious to know how actually you purified. That's one thing. And second one is actually you talked about rhodium TPP and also heterogeneous rhodium TPP and also rhodium TCP and also heterogenized. But if you take the TCP and the TPP, rhodium TPP and rhodium TCP, you do the reaction in a different kind of solvent, right? Because TPP is soluble only in non-polar solvent, whereas TCP is soluble in polar solvent. Yeah.
No. In the reaction, we have done with IPA. Now, most of the cases we have done with IPS only solvent.
So, in which case both are soluble.
Soluble, yeah, both are soluble. And in the heterogeneous catalyst, it is not solubility, it's not a matter. The main important is the IPS, it's again the hydrogen source. Because IPS hydrogen source, that is a preliminary step where the reaction is initiating. Because without IPA, the reaction will, we have tried with some other non-polar solvent like aprotic solvent. The reaction normally takes a little bit high time, duration required, initiation. So the IPA gives the proton, that gives the initiation of the, that's what we are believing. Yeah, and regarding the preparation, PCPP, we tried to wash with the pentane washing and remove all the impurities because most of the impurities are soluble in pentane, except your rhodium TCPP. The rhodium TCPP present as a solid powder inside the. We couldn't able to succeed on crystal formation. That is the main thing. But the thing is, when you wash with the pentane several times, it's like a tedious process. We have to wash till the make sure that the TLC is a single. We can simple pentane washing. We could be able to isolate, but then it takes a long time to remove all the impurities because all the impurities are soluble in pentane. That is one advantage we got it. So with that only we could be able to isolate.
Okay. Maybe one more question.
One
more question, Dr. Naveen. Am I permitted to ask one more question?
Yes, sir. Yes, sir. Yes, okay. Yes, sir.
I'm just curious to know how the rhodium TPP gets really heterogenized because it doesn't have any functional group and it got only probably it's coordinating to the 5th position and then getting wrapped. And whereas in TCP, there will be a strong bond with the matrix of your SBA. So
you are correct. Actually, the rhodium TPP, we from the mass spectra we confirmed that there is an axial portion having the halide. So that halide has been removed after the heterogenization. The axial portion halide has been removed and it is coordinated through the axial portion. In the case of rhodium TCPP, it is coordinating through the both sides. As you said, the carboxylate group is also on the carbamide. That is also we could be able to hear. And also there is an axial portion because the main thing is axial portion is getting coordinated in the this one because axial portion having the halide and that is removed when we try to heterogeneous on the surface. That is how it is coordinating on the surface.
Rhodium 2+ or rhodium 3+? I mean, after
rhodium 3+. No, it is 3+.
3+.
Okay. Based on the mass, because we couldn't able to get a crystal, we couldn't able to get it. But then based on the mass spectra, we could see that it is in rhodium 3+ because rhodium, there is a chlorine is there, extra chlorine is there. Okay. So that's what we confirmed.
Chlorine is probably coordinated to the 5th position, and you have the other side.
5th point. Okay. Yeah.
Great.
Other side solvent is there. Solvent is there. Solvent is there. The other side also solvent is there. So the mass is well confirmed. So, but then once he got a crystal, but then it was before we take into place for crystal analysis, we put the crystal has decomposed.
And one thing,
That's
and did you try to ponder on how actually the mechanism goes? I mean, how does it work? All these reaction, actually, you have a kind of a proposed mechanism by which all these reactions are happening. Is that possible?
So actually,
and
I wanted to add something to that.
Homogeneous.
So how this mechanism is like different from the homogeneous system, and are we getting like a kind of channelized version because of heterogeneous?
The mechanism is see, it is very difficult to confirm the mechanism in the heterogeneous case. But then what is we speculated, the sixth question is where the active sites can come, basically, where the sixth question oxyl, because there is a carboxylate group is that oxygen is going to coordinate with the metal center. That's how there are some literature in the previous based on that also we have proposed that, but then one has to. We have to. It is working, but we have to find out that what exactly happening. The heterogeneous system. We need to work it out a little more elaborate to see the mechanism as well. Maybe the what I feel is that perforin may be in the puckered shape. The metal may be away from the perforin, the cavity. That may be the reason it works in the heterogeneous step, because your fifth axial portion also pulled by the that is also coordinating, and then your metal is trying to pull away from the perforin, and there it's going to be exposed on the active sites, and it works. That's what we proposed in the paper also. But still, it has to some evidence we have to create.
Okay, sir.
Hello.
Thank you. Is there any other questions from students? Actually, I know you will have a lot of things going in your mind. But yeah, feel free to ask if you have any questions. Anybody? Okay, so then, let's all thank Professor Sakthivel for his wonderful talk. Thank you very much, sir.
Thank you, Naveen. Naveen, if you're with your permission, because I have 10:30 some meeting is there. So till 10:30 I'll be here, and I will join you later after the meeting. I'll join maybe.
Okay, sir. Okay. Thank you very much for joining.
Yeah.
Okay, guys, so let's move on. So now I think we'll have our second speaker, Dr. Sharma. Sharma, you are online? Yeah, I see. I think Sharma is there.
Hello.
Yeah. Oh, yes. Okay, so this is Dr. Sharma, SRK Yamijala. He is currently working as a postdoctoral research associate at University of California, Riverside. He's actually working with Professor Brian Wong. He obtained his MSc and PhD from GNCASR, Bangalore, under the supervision of Professor Swapan Pati. So he completed his PhD in 2016, and then he moved to University of Rochester to do his first postdoc with Professor Huo. And then later he moved to University of California at Riverside, where he is currently working. His areas of primary interest are computational and material science. He has about 18 plus international peer-reviewed papers to his credit. I think most of you might have read his article, which was published in our the online magazine we have, Rasatantra. So he wrote a wonderful article for us, Chemistry Inside a Computer. I think most of our students might have read it. If not, then please go and read it. So it's so nice. So we are very happy to have you with us, Sharma. So today I think he'll be talking about real-time degradation dynamics of hydrated per and polyfluoroalkyl substances in the presence of excess electrons. So, over to you, Sharma.
Thank you. So are you able to see my screen right now? Like
yes.
The acknowledgement
yes.
slide? Okay.
Yes.
Okay.
Yes. Yes.
Okay. Thank you. Good morning and namaste to all of you. I am Chaitanya, and I would like to begin my talk by thanking Dr. Naveen Kulkarni and the Chemistry Department of Amrita Vishwavidyapeetham for providing me this opportunity to present my research in this online symposium named Multifacets of Chemistry. I would also like to thank Professor Brian Wong and Dr. Ravindra Shinde, who is my colleague, for their contributions to this work. And I would like to thank Army Research Office and Department of Energy for funding. Moving on to the research part of this talk. In this work, we have studied the perfluoroalkyl substances. So these are the substances which are harmful pollutants which are present in the environment, especially in various drinking water resources. So in this study, we have used ab initio molecular dynamic simulations in order to study the dissociation behavior of these perfluoroalkyl substances in the presence of excess electrons. So when we are adding additional electrons, you can see this as a reducing environment. So we are studying here the real-time degradation dynamics of these harmful substances in the presence of excess electrons. So indeed, this is the first study to see the complete dynamics of this complete reaction process. And this work has been recently accepted in PCCP as a communication. And it also appeared as a front cover. It also appeared as like in various news articles in Chemistry World, physics.org and other places. So the first question which comes is like, what are perfluoroalkyl substances? So most of you might already know what are alkyl substances which have like a carbon backbone, and there will be several CH bonds in the system. So if we replace each one of these hydrogen atoms in the alkyl substance with a fluorine atom, then we will be generating a perfluoroalkyl substance. So on the left side, I'm showing here an octanoic acid. On the right side, you can see a perfluorooctanoic acid. So the speciality of these perfluoroalkyl substances is they have these carbon fluorine bonds, and in organic chemistry, carbon is the one which forms a strongest bond with the fluorine. So because of this strong carbon fluorine bonds, perfluoroalkyl substances are very less reactive towards any other substances. Also, you can compare the carbon fluorine bond strength with respect to the carbon hydrogen, and you can clearly see that it is roughly 30 kilocalorie per mole higher in energy when compared to the carbon hydrogen bond strength. Note that like 0.6 kilocalorie per mole is roughly our room temperature. So this means the carbon fluorine bond strength is roughly 50 times more than that of the carbon hydrogen bond strength. So as mentioned, due to the superior stability of these carbon fluorine bonds, perfluoroalkyl substances, whether it is PFOA or any other perfluoroalkyl substances, they will be very, very less reactive. And PFOA and PFOS are the most common perfluoroalkyl substances present in the our environment right now as pollutants, where PFOS corresponds to perfluorosulfanoic acid and PFOA corresponds to perfluorooctanoic acid. And due to this immense strength of the carbon fluorine bond, industrial sector has used this or utilized this carbon fluorine strength in order to prepare various kinds of consumer and industrial goods. For example, paints they have prepared, and these perfluoroalkyl substances are used in non-stick cookware. They will be used in fast food packaging and even in firefighting foams. And there are various other applications also for this perfluoroalkyl substances. And due to this wide usage of these perfluoroalkyl substances, we will see these perfluoroalkyl substances as pollutants in our environment, especially in the drinking water resources. So in this article, which was published in 2016, they have clearly shown various hydrological units or the drinking water resources in USA. And you can see in this figure, the left side figure with the blue color patches. So these are the ones where they have detected the perfluoroalkyl substances in the drinking water resources. So these sites, these blue color sites corresponds to industrial sites. For example, the industries such as painting and others, and also military training areas. So in the military training areas, generally there will be they train the soldiers in order to extinguish the fires. So they have used a large amount of firefighting foams, and due to this reason, you can see a 30% of detectable perfluoroalkyl substances. Similarly, at the airports or wastewater treatments, they have always observed they have always detected these pollutants at enormous levels. So according to the United States Environmental Protection Agency, the advised lifetime limit, that is like for the whole life, you can have a maximum of 70 parts per trillion of perfluorosulfite or perfluorooctanoic acid, these perfluoroalkyl substances. So in order to give a rough estimate of parts per trillion, you can assume that if you think about the Indian population, it is roughly 100 crores or like 130 crores or so. So this is 100 crores is like 1 crore is 10 to the power of 7 and 100 crores is like 10 to the power of 9. So 1 parts per trillion is roughly like 1% from the whole Indian population. So that's the detectable. So if we are able to detect 70 parts per trillion, that itself is very harmful for the drinking, like for humans or any other organisms who are consuming this water. So similarly, on the right side figures, they have shown clearly how the sulfonic acid and perfluorooctanoic acid are present in various places, and you can clearly see that most of the places have detectable levels which are greater than that of the 70 parts per trillion that has been suggested by the US EPA regulations. Not only India, not only US, the perfluoroalkyl substance contamination is there worldwide, and especially you can see even in India, in Tamil Nadu state, in the Tirupur district, they have found recently in the 2016 paper, they have suggested that there are 3 particular areas where they found approximately 100 nanogram per liter, or nanogram per liter is nothing but parts per trillion. So they clearly observed that a huge amount of perfluoroalkyl substances in the drinking water resources. So in this particular Tirupur district, there are like many dye industries, and as I mentioned in the examples, so perfluoroalkyl substances can also be used in the dye industries. So due to this reason, we are observing an increased amount of this contamination in the drinking water resources. So due to the consumption of these water resources, the very strength of the carbon fluorine bond that we have used is also becoming a curse to the human society. Due to the consumption of this water from these contaminated sources, it starts accumulating in our body. So why it is accumulating is because none of our organs are evolved enough, not only our human organs, but even like any bacteria or fungi are not evolved enough to dissociate this very strong CF bond. So these CF bonds are actually man-made compounds. Like enzymes are able to dissociate the compounds which are already present in the nature because they have evolved for many years in order to dissociate them. Whereas these compounds are man-made compounds and our biological systems are not evolved enough to dissociate them. And in this paper, they have clearly shown based on the human tissues from 5 human beings, and they have considered 20 residents and 20 various kinds of tissues they have considered, and they found that like the PFAS concentrations are available or accumulations are available in lung, brain, bone, and various other things. So due to this reason, it is very clear that once we have accumulated these things, so this cannot be secreted through our urine or any other excretia. So the main problem is these will be accumulated in our body and they will be present there. So it is very important for us to treat the water before drinking for this PFAS systems, PFAS substances. So earlier, very recent experimental results have suggested that if we use excess electrons or using a reducing environments can help us to dissociate these molecules. So on the left side picture, I have shown how these researchers have used cobaltamine, where the cobalt complex is able to donate the electrons to this perfluoroalkyl substance, and they have shown, although they did not discuss any mechanism for this system, they have shown that most of the fluorine bonds, so 16 out of 19 carbon fluorine bonds, could be cleaved in this particular by using this particular catalyst. They have also synthesized a artificial cobalt porphyrin complex, and using that also they were able to show that there is a possibility to degrade this complete compound. Similarly, there is another study where they have used a carbon nanotube electrode, and they have they absorbed the carbon nanotube electrode will be able to absorb this perfluoroalkyl substance, and subsequently they will shine this system with the UV light, which will generate the hydrated electrons or solvated electrons. The electrons will be solvated in the water, and these hydrated electrons can go and interact with these perfluoroalkyl substances, and they can further degrade it or dissociate this complete compound. So inspired by these two studies, we have started asking the question of what is the exact mechanism for the degradation mechanism of this solvated p phases in the presence of excess electrons. So earlier studies have suggested that they will degrade, but none of them have suggested or given any clear mechanism for the degradation process. So for those students who do not know anything about the simulation, I would like to just give 2 slides to introduce you to how do we do the simulations. So if you consider these are like perfluorooctanoic acid and this is perfluorooctane sulfanoic acid. So you can simply imagine whatever the molecule or the material you have as simply as a bunch of atoms, which means they are m number of nuclei and n number of electrons which are interacting with each other. So you can assume that you all know that in order to compute energy of any system, you can divide the energy into kinetic energy of the system and potential energy of the system. So here you can assume that your system has only m number of nuclei and n number of electrons. So now the kinetic energy of the system will be calculated based on the nuclear motion. And similarly, the kinetic energy of the electrons will also be considered. The other interactions which come between these two, such as nuclear potential interaction, and similarly the electron interactions and electron nuclei interactions. So these kind of interactions will be considered as the potential energy related interactions, and the kinetic energy is just the movement of the ions. So with this simple picture in your mind, one can in general consider 2 particular kinds of scenarios. If you have already taken any quantum chemistry course, you might be already aware of the Schrodinger equation. And so there will be 2 particular processes that you can simulate. First kind of simulation is you have a fixed set of nuclei and you will be optimizing the electronic positions. And for this particular set of nuclear coordinates, you will get the system's energy. And there is a second kind of scenario where the nuclei are also evolving simultaneously, electrons are also moving. So this is like a picture where both the electrons as well as the nuclei are moving. So if you assume that sun is also rotating and the planets are also rotating, so that kind of a picture you can have here. So this kind of problems are solved using the time dependent Schrodinger equation, and the current problem which I'm solving, which includes the dynamics of the system, dynamics of the nuclei, is related to this one, but we are dealing with a special case of this nuclear dynamics or time dependent Schrodinger equation method. With this brief introduction to the methods, I would like to mention the real simulation steps. So what we have done is we have solvated this perfluoroalkyl substances in 43 water molecules using a software called PackMol, and then we optimized each of these structures. So here optimization means we have a fixed set of nuclear coordinates and we are optimizing the geometry positions at each and every step. And finally, we will obtain the electronic optimized electronic coordinates for that particular fixed set of nuclei. So we used the DFT PB exchange correlation functional along with the Grimm's dispersion interactions as well as the double zeta basis sets in order to optimize this whole structures. So as the excess electrons can lead to spurious self-interaction corrections. So we have also self-interaction errors. So we have corrected that self-interaction corrections using the average density self-interaction correction, which we have also further tuned for the alpha and beta values. These are specific details. If you have any doubts, I can discuss about them. But this is what we will be doing. And once we obtain the optimized structures of these systems, then we run the NVT simulations at 300 Kelvin, which corresponds to roughly our room temperature, until it equilibrates. So this NVT equilibration run will be run for several picoseconds, and which will generate several configurations. And we use these different configurations from the NVT in order to perform the microcanonical ensemble simulations using a 0.5 femtosecond of time step, and then we add the charges. So roughly these are the different kinds of systems that I have considered. So here on the left side, I have shown you the charge is equals to 0. So where the PFOA and PFOS molecules are solvated inside this water. And then you can clearly also see that none of these molecules are dissociated. There is no CF bond is dissociated on the leftmost figure, suggesting the robustness of this result as well as the very high strength of the CF bonds. However, once we start adding the electrons to the system, you can clearly see that for the charge -1, you can see a dissociation of 1 CF bond, whereas for the case of charge -2, you can see the dissociation of 2 CF bonds. So thus we found like there is a proportionality relation between the number of electrons added to the system and number of ions dissociated in the the CF bonds dissociated in the system. We are also able to unambiguously show that excess electrons alone can lead to the CF bond dissociation. Even in the NVT normal NVE simulations with charge 0, you can see that the complete sulfonic acid do not have this proton here, which is majorly because it's an acidic compound, so automatically it should lose the proton to the solvent, and it is indeed losing the proton to the system. We have so this whole simulation setup clearly suggests us that if we add excess electrons to this perfluoroalkyl substances which are solvated in the water, then there will be a dissociation of these compounds. So this is the first important point of our work. Next, we examined also the dissociation timescales for these systems. So you can clearly, here we have plotted the carbon fluorine bond distances for each one of these compounds, and you can clearly see that all of these graphs are starting at 1.3 angstroms, as you can clearly see. So this corresponds to the equilibrium carbon fluorine bond strength. So as we are moving on the simulation, you can clearly see that there is an increase in the bond distance, suggesting the complete dissociation of the CF bond. Furthermore, we can also see that in the inserts of each of these graphs, within the first 100 femtoseconds, the CF bond is completely dissociated. The bond distance has changed from 1.3 to 2.5, which is like 1.2 angstroms of bond distance increment. So this clearly suggests that not only the excess electrons dissociate the perfluoroalkyl substances, but they dissociate them in less than 100 femtoseconds. That is, an ultra fast dissociation happens in the presence of excess electrons. We have conducted the similar kind of simulation, 16 different simulation setups we have considered, and in all these cases we have clearly shown that this ultra fast dissociation always occurs. Also note on the right side figure, I have given the dissociation mechanism, dissociated carbon fluorine bonds for PFOA and PFOS molecules. So clearly you can see that the bonds which are dissociated are completely different ones. So here it is C3F15, here it is C1F3, something like that. So when we have changed different kinds of configurations, we found that the carbon fluorine bonds which are dissociated are completely different, but in all the cases, we consistently observed that CF bonds will dissociate with the addition of excess electrons. So to further examine this, we have plotted the spin densities of the system. As you can see here, the entire spin density when we add one additional electron to the system is localized on the PFOA molecule or the PFOS molecule. And as the simulation proceeds, the spin density is slowly accumulated at the site of dissociation. This clearly explains the earlier result. Because the initial spin density is entirely localized on the complete PFOA molecule, all the CF bonds are weakened. So any of the CF bonds can be easily dissociated, and that's the reason for observing different CF bonds being dissociated in different simulation setups. So this clearly explains that earlier result. For the case of 2 electron addition, we observe two kinds of dissociation. One, we are naming it as trans elimination. Another one is we are naming as the cis elimination, depending on how the fluorine atoms are moving away from the carbon-carbon bond. Here, in the case of trans elimination, each of these fluorine atoms are moving in a trans manner. For the cis, it is in the cis manner. In both of these cases, you can clearly notice that there is a clear up and down spin density in the beginning. That is, there is a spin polarization in the system when you are starting the simulation. However, the such spin polarization is completely quenched when you are using the when there is a trans type elimination, whereas that spin polarization is retained in the cis type elimination. So out of 16 NVE simulations, 16 microcanonical ensemble simulations that we have performed, 12 of them have shown that there is a trans elimination in the system. And earlier calculations were not able to explain the site of dissociation, but we, based on our spin density simulations, we are able to explain it, explain this particular result. So basically, we are saying here that due to the majority of the simulations are leading to the trans type elimination, we expect that the final product or the original reaction mechanisms could involve this trans type elimination. We further plotted the charge as well as the spin fluctuations in the system, and you can see for both the trans as well as the cis eliminations, the charge fluctuations are roughly similar, and they are leading to the formation, like there is a gain in the minus 0.7 electrons for the fluorine atoms. So when the carbon fluorine bonds are dissociated, it is the fluorine atom which is obtaining the charge, whereas the carbon atom is the one which is obtaining the spin in this particular case. And you can clearly see that only for the case of cis type elimination, which is given in the bottom figure, there is a clear spin density, which is 0.8 or so up spin density and 0.8 down spin density. Although the entire spin density, if you consider up plus down, it is 0, there is a spin moment is still there. So this is much like your antiferromagnetic type interaction here. Whereas in the case of trans, due to the annihilation of these spins to form this C double bond C bond, there is no spin at the end of the simulation. So based on all of these results, we suggest that C double bond C is formed only with the trans elimination, and this product will be the major product. So this result is also supported by earlier experiments where they suggested that the presence of C double bond C can enhance the dissociation of the system. So as our excess electrons are showing the formation of the C double bond C, and already earlier experiments have shown that reduced environments can lead to the dissociation of these perfluoroalkyl substances. We conjecture that the C double bond C intermediate would be a prime one or a very important one. Here is our simulation result clearly showing the formation of C double bond C with a bond length of 1.29, whereas in the normal case it will be around 1.5. And we also formed the formation of the HF intermediate. So this HF intermediate could be stable or it might dissociate because this is an acidic proton, and because of the solvation environment, after some time of the equilibration, it could again dissociate. So with this, I would like to conclude the talk. We have shown clearly that this is the first real-time dynamical study of PFAS degradation with excess electrons, and we were able to show that the presence of excess electrons can enable the dissociation of the strongest CF bonds. So you remember that, like, in this particular complete molecule, there could be CC bond dissociation or CF bond dissociation or CO bond dissociations. But what we have specifically shown is using the additional electrons, we can specifically dissociate this CF bonds. Similarly, we also shown that not only the additional electrons dissociate the CF bonds, but they also dissociate them in ultra fast manner. Finally, we have conjectured that the trans type CF elimination is the most probable intermediate that will be present in this system. With that, I would like to thank you all for your attention, and I would be happy to take any questions.
Thank you very much, Dr. Sharma. Actually, yeah, so I know it's hard to explain the theory works, but you made it look so simple, and I think everybody got a glimpse of it. We're very thankful for you for that. I think now we have time for maybe a couple of questions.
Thank you, Naveen.
Naveen, can you hear me?
Yes, sir. Yes, sir.
Dr. Sharma, thank you for your lecture.
Thank you, Professor. Thank you, Professor.
I should say this is a layman's question, because
okay.
Talk in terms of the molecular orbital theory point of view. Your interaction or reaction is nothing but you're doing the reduction. You're putting electron in the molecule, and
correct.
This is a saturated system, except your the side group, function group. I omit that part, and you have a saturated system. You have a CC. Now, putting electron means electron going into one of the lumos.
Correct, Professor.
Okay, so it could be there are CC sigma star and CH sigma star and CF sigma star. Now, I'd like to know which is the LUMO of this molecule. If you take this small molecule, which is the LUMO?
So the LUMO of the entire system looks like this, Professor. So it's not like simple CF bonds. The LUMO of the entire system is actually localized on this perfluoroalkyl system. Complete system, it will be localized. So you should also notice that we are considering a solvated system.
Delocalized, is it? Or
it is delocalized on the entire system, and that's the reason for all the CF bonds to be at a time like weakened. The weakening effect of all the CF bonds is observed in other calculations, which I have not shown here. Because the LUMO is completely delocalized over the entire system, all the carbon fluorine bonds are at a time weakened.
I just ask you because you have a CF bond which is stronger. So the sigma CF is bond is the lowest in energy, and correspondingly sigma star CF will be the highest. Really even higher than that of sigma CC or sigma CH. So
it's very possible.
Rather, of course, you may talk about delocalization, but of course, we talk in terms of centering on one of the lumos, it will be mostly based on the either sigma CC star or sigma star CH rather than sigma star CF. So I'm talking about whether the bond fission, does it happen on either CC bond fission or CH bond fission or CF bond fission, which is more favored on putting electron or reducing electron.
So if you are considering just this isolated, CF only CF molecule as such, then whatever you are saying is correct. Then it could be directly going to the CC bond dissociation. However, because we are considering it as a whole molecule, after the addition of the electron, if for example, if you are assuming that a CC bond is cleaved, so then that additional electron also should be stabilized. So in order for that additional electron to be stabilized, it favors more to be there on the fluorine rather than on the carbon. So while the additional electron, as you are expecting, can go to the CC sigma star, and it can lead to the dissociation of the CC bond. But once after the dissociation also, we should also consider, right? So once this additional electron has gone to the CC sigma bond and it tries to dissociate that CC sigma bond, then both of these carbon atoms are like roughly neutral. If you want to say, or like homolytic fission is the only possibility. But once you have added this electron, it's more like a negative charge is there, and it more prefers to go to the fluorine atom such that it can dissociate. So once these all bonds are weakened and once it wants to dissociate, that could be one of the ways to explain that CF bond is more ready to dissociate than the CC bond. This is my way of like explaining to your question.
This is initial, in other words, the initial step will be CC bond breaking, and followed by you have an anion there, and then further that quickly the CF bond. Is that right?
We can think that way, but like in reality, at least during our simulation, it is not the way. It is directly CF bond is the one which is dissociating, Professor.
Is there any experiment? You talked about some experiment.
Definitely, they cannot tell about the mechanism of this CF bond dissociation. But what they have clearly measured is the So in this system they have measured the fluoride ion. They have measured the content of the fluoride ions in their experiment. That's what they have measured, either in this one or in this one. They clearly found that this whole PFOS system is dissociated and they have measured the content of the fluorides. That's all they have measured.
And no other species other than fluoride, there is no other.
They did measure in this particular case, they have also found this SO3 dissociation, but in our case, we did not observe that. And they did even find the formation of lower alkyl chains, which includes the CC bond dissociation. But during our simulation time, it's just the CF bond which is dissociated.
Dr. Sharma, did you see any trend in this cleavage, like primary, secondary, and tertiary? Like, is there any comparison which goes first?
Yes,
because there should be.
Yes, definitely.
I don't know if you explained that. Yeah, I
did not explain it, but so we always observed the formation of the secondary bonds being dissociated rather than the primary ones. So when we calculate the bond dissociation energy for this primary ones, we found that these are very strong when compared to the secondary carbon fluorine bonds. So, and in all the cases, like only one carbon is only there with the primary type of carbon, right? So this carbon fluorine bond was never dissociated in our 16 NV simulations that we have performed. So it was always the secondary bond that has broken.
Okay. If you try to add more electrons, and is it possible to like channelize kind of like we think about this specific reactions, right? So can you try to do it only on the primary rather than the secondary? Theoretically, I don't know. Experimentally, we always try to do something like that to get the specific.
Sure. So at this moment, like so theories are there where we can completely localize, but I have not done any of these kind of things. Like when we are adding the electron, it's like on the entire system we are adding an additional charge. So where it goes, we are leaving it to the quantum mechanical behavior rather than like addressing directly localizing that electron to a particular moiety of the group in these simulations. But there are other simulation methods where you can actually localize it on the particular place of the entire system, and then you can study. So there are like we are studying at this moment, like I did not show these results, but we are trying to localize the electron in the solvent and leave that electron there, and we allowed it to directly interact with the system. And in these cases also you can see, so this is electron cloud. So electron cannot be seen as a particle, but like a wave here or electron cloud. You can clearly see that as the simulation proceeds, slowly the electron is diffusing and it is like going on to the entire system again here also. And further if we continue the simulation further, we are able to see the dissociation of the electron. But at this moment, we did not completely localize it to attack at a specific place, like what I hope this is what you are trying to say, like specific moiety you want to put the electron on, and then you want to see the reactivity of that specific moiety.
Yeah.
Either. So that case, that calculations I have not done, but these are possible to do for sure.
Dr. Naveen, I have one more short question. Is it okay?
Yes, sir. Yes, sir.
Okay, Dr. Sharma, what kind of reducing agent did they use? I mean, you said there is an experimental report. What is the reducing agent they have used to put electron or to break this bond?
Sure. So in this case, they have generated what are called as this hydrated electrons. So what they did was like they put this iodide I- or sulfate ions in the water, and they shine this UV light on them. So this is the way to generate this hydrated electrons, and the other electrons which are just went into the system through this potential. So they have just made the CNT electrode, and they have used the external potential to generate the electrons. So the hydrated electrons are generated using this UV light, shining the UV light into the iodide or sulfate solvated water.
Okay, thank you.
Thank you, Professor.
Thank you very much, Sharma. Do we have any more questions? Maybe we can take one more question if anybody.
Sure.
Okay, so I think there are no more questions. So let's thank Dr. Sharma for his wonderful talk.
Thank you, Naveen. See you.
Thank you much.
Bye. Bye.
Okay, so let's move on to the third speaker. We'll have Dr. Dandamudi Lenin. So Lenin, are you online? Dr. Lenin?
Perhaps he's
yes, sir.
Seems to be having some issue.
Okay. No, I think he's online. Lenin, can we see you? Turn on the video if possible. I think it's raining everywhere, so
yeah, it's raining there also. Amardapuri, here it's fine. It's like morning. It was very heavy rain, actually, sir.
Now it stopped, sir, but yeah, it was raining.
Okay.
To see. Okay, Lenin, can you please turn on the video?
Video is on. Not only thing is the mic is not working.
Let me contact some maybe technical issue. Dr. Lenin, I think you have to unmute your speaker. We don't see you here. I don't know.
Naveen,
Hello?
yes, he might be not unmuting. You can call him and tell.
Yes, sir. I'm trying to reach him, but I think it's network issue. So
Okay.
let me try. Yes, sir.
Lenin also said heavily, so there might be some problem also.
Naveen sir, you can text him here.
I think there was some electricity problem, so he will be joining us soon. I just called him, so let's wait for two more minutes. Sorry for the wait. I think he'll be joining us. Maybe then we can actually go with Dr. Animesh Das if he is online. Dr. Animesh, are you online? Animesh?
Hello.
Yes, Animesh. So I
Yes.
think Lenin is having some issues with the network and connectivity. So maybe
Okay.
we can go with you first, and then when everything is said, then he can come back. Is that okay for you to go now?
Yeah, no, no, it's yeah.
Okay. Thank you. So I'll just make a quick call to him, and then we'll start with Dr. Animesh Das.
Okay.
Okay, sorry for all the delay. Dr. Lenin had some issues with the connectivity, so he could not join us now, but I think we will have him later. So we will have now Dr. Animesh Das presenting his work. So he's currently working as an assistant professor at Department of Chemistry, IIT Guwahati. So he's there from 2015. He received his MSc from IIT Kanpur and he joined University of Göttingen, Germany to pursue his PhD studies under the guidance of Professor Frank Mayer. Later, he moved to University of Frankfurt, Germany to work with Professor Matthias Wagner for his first postdoc. And later he moved to University of Texas at Arlington to work with Professor Rasika Dias for his second postdoctoral work. So he has over 20 plus publications in high impact journals. His research interests include transition metal organometallic chemistry and catalysis. So today I'll be talking about transition metal free regioselective CH bonds, cyanation, and chemoselective reduction of fused azides. So we're very happy to have you here, Dr. Animesh Das. So it's over to you now.
Thank you very much, Naveen, for your kind introduction, and thank you very much also from your university. What a opportunity to give some preliminary results. So today, actually, I'm going to talk about. Wait a moment, just I'm going to share it. Now, can you see the screen? Hello.
Yes, Animesh.
Now, can you see the slides?
Yes, you can go ahead.
Okay. So today I'm going to talk about the title of this talk is Transition Metal-Free Regioselective CH bond cyanation and Chemoselective Reduction of Fused Azides. So actually we are interested in this work, the transition metal free mediated two works basically. One is regioselective cyanation approach, another is chemoselective reduction of fused agents. So why the transition metal free? Firstly, the transition metals actually, if you have it, so often you have some kind of an toxicity problem while actually you do the late stage modification of drugs in the last stage. So there is some kind of a troublesome. So it would be worth it to have it some kind of a metal-free contaminated approach so that problem can be avoided. So in this talk, actually, there is a two-part. One is the regioselective CH bond cyanation, and another is the chemoselective reduction of agents. So first, I'm going to talk about the first part. So before to go for that, first we have to know what is agents. Agents is actually nitrogen-containing 6-member heteroaromatic compounds. For instance, you know that this is pyridine, also agent class of compound. So what is fused agents? The fused agent means there is another ring which is fused in this ring system. So under that there will be might be quinoline, isoquinoline, quinoxaline, or naphthalidine, all are like a fused agent class of compound. So we are interested towards that quinoline-based compounds. As you know that this quinine is a very well-known antimalarial drug. So recently, you might found that hydroxychloroquine or chloroquine also very, found to be well suitable for this COVID-19. So in this regard, actually, we are interested for this quinoline motif. However, if you see that in this quinoline motif case, the C2 positions can be detoxified due to hydroxylation under physiological condition. So therefore, scientific community are interested to develop some kind of a quinoline motif where that C2 position can be functionalized so that this kind of a detoxification can be blocked. So in this regard, we are interested actually to position cyanide, nitrile functionalization approach. So the question is why nitrile? The nitrile, obviously, there are several reasons to do that. One part probably that organic synthetic point of view, nitrile one can easily functionalize it to nitrile to acetone, amide, acid, or ketone, so on. But in nature, you or in that protein backbone crystal structure, you could see that actually in the protein crystal structure, you could see that nitriles where there is a nitrogen lone pair which have some kind of a hydrogen bond participation is there with the amino acid, or even that in the protein, whatever the water is there, there is a reasonable hydrogen bonding is there, and that way the that nitrile is also helps. On the other hand, that nitrile is also reasonably stable in the body. So in this regard, we want to develop something where is a C2 position nitrile functionalization. However, if you will see in this ring, there is one is electron deficient ring, another is normal aromatic ring. So as you know that electron deficient rings, as it is electron deficient, so the nucleophilic substitution reaction can occur easily. However, there is a selectivity issue could be there. One is C2, another is C4, but I have assigned it here. So that is one of that challenge. But if you could see that as the nitrogen is close proximity, so might be one can think about that more selectivity one can expect C2 position over the C4 position. So in this regard, you could see that there is a several kind of an nitrile or nitrile based different kind of an functionalized derivative with a heterocyclic scaffold is known in the literature. Those are potent bioactive molecule. So not only those are pharmaceutical point of view, those are also in the agrochemical industry purpose people have used. So if you look at it, actually this nitrile functionalized compound synthetic approach, so even that compound like a simple 2-cyanopyridine or 2-cyano based kind of a pyridine compound, it is very well known. Like if you look at that, that one actually one can easily make it by simply 2-bromo or 2-halo pyridine or 2-cyano compound by this Sandmeyer approach. But in that case, you need a pre-functionalization heterocyclic moiety. But recently, Hartwig and co-workers, they found that directly one can synthesize that same pyridine or quinoline kind of or any other heterocyclic based compound. They managed it using a silver fluoride as an activator and potassium cyanide as a cyanide source. In this case, what they found that silver chloride, it is activated the ring and form a 2-fluoro heteroatic moiety, and then nitrile is simply nucleophilic reaction happen. However, if you look at it, there is also some transition metal free approach is also known in the literature. So if you use the triplylic anhydride, so that triplylic anhydride can also activate the nitrogen, and then also under in presence of base to rearomatization way, you can have that nitrile compound. But there is one problem, there is a selectivity problem, like C2 and C4, both can be possible. So to overcome that selectivity, people are interested towards that N oxide, which one can easily make it from that simple oxidation from that quinoline or pyridine to N oxide by either MCPBA or peroxide and so on. So as this N oxide is a dipole, 1,3 dipole kind of change, so that C2 is more electropositive character. So basically, if you have it any mild activating agent or so on, so that nucleophile can react at the C2 position and followed by in presence of base to rearomatization, you will have it a final nitrile compound. So in the literature, you could see that various kind of an activator or different kind of an base is known where this nitrile can be made it by using an N oxide. And in addition, there is also sometimes people use it also some halogenated solvent. So here we are interested to develop something which is not additional activator, base or solvent and so on. So in this case, what we first tried, like a simple N oxide we have taken and with the TMS cyanide, which is commercially available, and just simply if you mix it together in neat condition and give a heat at 130 degree, around 1 hour, you will have it a very quantitative or excellent yield, I should say. You will have it a 2-nitrile compound. But the reactions duration also you can reduce it if you do the reaction within 5 minutes in microwave under the same condition. So basically it is a very good approach. If you could see that there we are not require any other additional activator, even solvent or base and so on. So using this approach, actually we could make it actually various functional group containing nitrile derivative. One can see that in 2G compound where that ketal kind of compound is also nicely survived there, and also especially 3 positions or 8 positions. This is a 3 position, this is 8 position. This is a 3 position, this is 8 position. You could see that this is because of the bulkiness. Sometimes there is a problem, but in this protocol, we can nicely manage it actually, those functional group. And if you look at it, actually 4,7-dichloroanoxide, if you use the, the precursor, where that 4 position chloro is intact, cyanide was not functionalized over there. Only that selectively C2 position will be functionalized. Moreover, if you see in that bis N-oxide case, there is a selectively one is nitrile functionalized and have other side was not functionalized. So one can also do some other tunable chemistry over that side. So using this methodology, actually, if you could see that this is not only for quinoline or it could be also applicable with some other heteroaromatic N-oxides. So it could be also applicable for isoquinoline, naphthalidine, pyridine as well. Okay. So the variation of other heteroaromatic N-oxide could be also applicable. We also showed it here also different kind of an chemoselective approach, the cyanation approach. How we will manage it? Our starting material was a 3-bromoquinoline, where in metal-free pathway we also made it a selectively C4 position keto functionalized, and then under the same condition using our approach to selectively functionalize it. Hello. Hello.
Yes, Animesh, I think you can continue.
Okay. So here actually you could see that chemoselectively one can be also cyanation can be done. So using this protocol, we also showed it actually different kind of an pharmaceutical based compound also we made it in a one pot. You could see that example B and example C and example D as well. You could see that we started from directly from quinoline in one pot. We made a enoxide and then applied our protocol to have it a quantitative manner. This two cyano heterocyclic compound, and those also can be in one pot. We also could be hydrolyzed under acidic condition to get a simple TB inhibitor, compound 8. So in addition that, if you could see that those compounds, some of the compound is also very useful in agrochemical industry, like you could see that compound 9, where this is a very important precursor. One can easily make it in a one pot using our protocol. And this protocol is not only for in a 100 or 200 milligram scale. We also checked in a gram scale. It also works well in this case. So now if you will see that it is always worth it to look at it whether that is a possible to functionalize any kind of a late stage modification of any drug or not. In this case, we also checked it quinine derivative. In this case also quinine derivative is also working well, where you could see that the free OH is also there intact. In that case also we could nicely functionalize it to nitrile compound. In addition, we also functionalize it 4-position tocopherol derivative offering this using this protocol. So the proposed mechanism could be like this way, that TMS cyanide will react with your TMS, enoxide will react with TMS cyanide first, and this forming like a OTMS attack and cyanide as a nucleophile that will attack to that electropositive C2 center, and they are followed by a rearomatization way, and then you will have a 2-cyano compound. But you if you would see in this mechanism, actually you need a 2 equivalent of TMS cyanide. One, you need to activate that enoxide. Another, you need this cyanide, whatever you have it, and that is further activated by OTMS to have it that. So in this case, one side product you could see that TMS to OTMS, but HCN is one of the bad side product obviously. But for that, we also developed a proper quenching protocol so that it will be there will be no any kind of toxicity behavior and so on is there. Currently also, we are also using that whatever in situ HCN is forming to develop in one pot some other HCN based functionalization approach. So if you could see that the TMS cyanide basically has a dual role, which can act as a cyanide source as well as a activating agent. So for this way, you don't need any kind of an additional activator, and also base for rearomatization, which can be done by simply heating instead of base. So that's the reason actually that process is a very operationally simple, highly efficient, economically viable, obviously, because you don't need any additional activator, base or solvent and so on. Especially hazardous solvent often in this kind of chemistry people are used, but here it is not at all required any solvent even. So that protocol even applicable for the, as I said, it is a late stage modification of bioactive molecule and so on. And also we believe that this is a first example that nitrile moiety is incorporated to that CH bond of the N-heteroaromatic compound in absence of any external activator and base. Just simply heating is enough to get those type of derivative. So I'm going to talk about in the next part, where is a boric acid catalyzed chemoselective reduction of quinoline. So that actually if you reduce the quinoline in the selective manner, then that whatever the ring is called it 1, 2, 3, 4 THQ framework, and that THQ molecule, it is a very potent bioactive molecule in different aspect, and sometimes it is also found in as a natural alkaloid. So in this regard, we are interested to develop some metal-free approach where that one can make it easily that 1, 2, 3, 4 THQ. In this case, if you should look at in the literature, there is a recent literature even in Chem Review, you could see that there is a several way one can make it a 1, 2, 3, 4 THQ derivative. However, we are interested towards directly started from quinoline to have it a 1, 2, 3, 4 THQ. But using this approach, if you look at in the literature, there is a mainly two class of way it is known in the literature. One is catalytic hydrogenation, direct hydrogenation with a transition metal or in metal free. Another is transfer hydrogenation using with metal or without metal. In this regard, if you look at in that molecular hydrogen Using a molecular hydrogen approach, obviously it's called a direct hydrogenation approach. So where often for hydrogenation, as it is a hydrogenation approach, so you need a kind of a high temperature and high pressure reaction for this kind of a protocol, and that's why you need a drastic condition for that. So to overcome this drastic condition, people are interested towards the like a mild condition. So in this regard, there is a recent approach in presence of molecular iodine with a BH pin under argon atmosphere. People could also manage it a THQ 1234 THQ derivative. However, this is not a economical hydride source, because you are actually stoichiometrically you are using that BH pin. So whatever the side product it is forming, it is called a BP no BP, and that you cannot actually recover it again. It's a waste. And this overall in this reaction, if you look at it, it's a little bit of super stoichiometric reaction of the people who use the BHP. And also it is not in a air stable reaction. You need to dry in everything. So it's not in practical way. It is difficult to make it that 1234 THQ in this way. So there is also literature like a B C6F5 it's a organoboron, and using this organoboron, there is a multi-step way one can make it a 1,2,3 PHQ, 1,2,3,4 THQ. In this case, you could see that as it is organoboron compound, so this BC6F5 it is actually a moisture sensitive boron catalysis. And also if you look at this BH pin, it is also like a sensitive hydride source. So basically, as those precursor is your sensitive, so you need to dry it, all the solvent, and also your starting material also to be proper way you have to do it. And in this case, if you look at it, as this B6F5 is a potent Lewis acid, it's just so that actually that substrate tolerance, especially the reducible functional group tolerance, it is lacking in this protocol. So our approach towards in this direction, where we try to make it some kind of an other alternative instead of B6F5 and as well as instead of BH pin, whatever the hydride source or saline source people are using, instead of that some other hydride source. In this regard, what we planning to do, instead of B6F5 whether it is a simple boric acid or boronic acid, whatever the back and B orbital is there, can it be used as it enough acts as a Lewis acid to get it that. So because one hand it is a cost wise, it is a much cheaper if you compare with the B6F5 and boric acid, and another thing is like that sensitivity and functional group tolerance, so mild condition might be one can get it. And secondly, also you have to think it that hydrogen source. In this case, we are interested that hand ester. This hand ester is not the new hydrogen source. It is already well known, well developed long back. But we are interested here because that two aspects. One is that hand ester one can easily rearomatize to generate the hydrogen. So that is really a very stable hydrogen source. You don't need a hydrogen gas cylinder or kind of a sensitive hydride reagent and so on. And also another hand, it is a really biomimic hydrogen source, like a NADH analog of that. So basically, our aim towards in this direction to have it a 1, 2, 3.
Animesh, sorry to we don't see the screen, I think. So can you share it again? Maybe some issue. I don't know what happened.
So cannot display content.
Yeah, so there is some issue. Please look that and then try.
Is it now? Can you see it now?
Wait a second. Yes. Now it's back.
So it's a boron-based Lewis acid. That slide is showing, like slide number 13, right?
Yes.
Okay.
So you can start.
So basically, there is a two reason we are interested. One, we actually change the Lewis acid, whatever that moisture sensitive and Lewis acid people have used. Organoboron B6F5 we are interested like a simple boric acid or boronic acid. And then secondly, whatever the hydrogen source or hydride source people have used, not hydrogen source, I should call it a hydride source, BHP or saline. In that regard, we are interested to use like a hand ester as a mild hydrogen source, and that would be really a bench stable reagent, air stable, and you can make it in a gram scale. There is no any issue, and that is also analog to the biomimetic hydrogen source. So in this regard, actually, the present protocol, there is a mainly two aspects it is useful. One is mild condition we are using hydrogen source, another is mild catalyst also boric acid. So using this approach we could make it really very good yield and quantitative manner. Quinoline to 1 to 3 pH3 which is simply 15 mole percentage of boric acid and Manchester 2.5 equivalent under 60 degree in DC solvent. So first we checked it a simple basic quinoline, it works well. And if you look at it, example 2H, there is also very good stereoselectivity is also there. That middle compound, compound 2H, and also there is a several other reducible functional group tolerance is also nicely works in this case. What previously was lacking in the literature in the previous condition. So if you could see that 2 position ester was nicely intact, especially halo compound, cyano compound, nitro compound, those can be reduced under that condition. So in this condition, it was nicely intact, even that allyl moiety, keto, alkyne, and so on. So in this case, also you could see that other n-heteroarenes is also nicely works using this way. Like you could see that below example 4A to 4D, and there is another interesting aspect. If you look at that, there is a, if you start with a 6 position aldehyde quinoline under the same condition, what we end up like a 6 position methyl THQ. In this case, there is some kind of an unprecedented reactivity observed. Basically, because of this boric acid, probably it works. Boric acid or boronic acid is called. So what happened? This aldehyde under that condition,
Animesh, sorry, again it broke. You again have to share the screen.
Is this okay now?
Yes. Please go ahead.
So if you start with a 6 position aldehyde quinoline, the end-up we have it as 6 methyl THQ. So what we propose that this aldehyde first reduced under that condition to have it a alcohol, and in presence of boric acid, this CH2OH eliminated alcohol, actually OH goes away and it's forming like a I2, and that I2 even we have characterized by NMR, and then followed by a reduction to have it a 2J. And then on the other hand, if you start with a 4,7 dichloroquinoline under the same condition, there is actually this 4 position chloro, you can see that it was not survived, it is a dehalogenation happened, and there is a compound 3H forming where that only 7 position chloro is intact, 4 is goes away. So we propose the mechanism probably like these two pathway, but none of the cases we have isolated that intermediate. Now, if you look at in the mechanism side, so what we first checked it actually that quinoline in presence of, there is some solubility problem actually, this boric acid in CDCl3. So that's the reason we have checked it phenyl boronic acid. So that was reasonably well soluble. So we mixed it together, and then what we found that C2 position proton and C2 position C4 positions proton, it is goes to in the downfield. So basically we are expecting that quinoline nitrogen might be weakly coordinated to that boron center of boronic acid. Then that is the reason might be C2 and C4 to sort of extent goes to the downfield. It has been strengthened or further concluded by the boron NMR. If you could see that simply boric acid whose boron NMR coming 29.6. Whereas if you mix it phenyl boronic acid plus Manchester, there was also no change. However, if you do that boronic acid plus quinoline moiety, where you found that it goes to that upfield. So probably the nitrogen lone pair is coordinated to that boron center, and it is a not real 4 coordinated species of the boron, but how to sort of extent there is an interaction between this quinoline and the boron, and that was the reason it goes to that upfield shifted. So then we have also done some kind of a deuterium leveling experiment. From there we understand that in presence of D2O, if you do the same experiment, where we found that this deuterium incorporation happened at C3 positions, which is actually exchangeable proton. So based on those experimental findings, we found that the catalytic cycle could be like this way. So what we have is like a phenyl boronic acid or boronic acid, which is actually coordinated by the pyridine or quinoline. Simply a coordinated adduct will form it, and then that coordinated adduct is basically, because of that coordinated adduct, this pyridine or quinoline to sort of extent it is activated. Now this Hanchester hydride, it is attacked to that C4 position of this quinoline, and then you have it a 1B, and that has been also characterized by stoichiometric NMR experiment. And then this 1B could be isomerized 1,4 to 1,2. Basically 1B to 1C is forming, and then followed by further reduction, you will have it a 1, 2, 3, 4 THQ plus aromatase Hanchester. Now there is also question, if you look at it, that aromatase Hanchester is the side product. Basically this part is forming as a side product. So how one can overcome it? So in this case, there is a two way we have done it. One is, in this case, I'm going to show it a simple sodium cyanoborohydride. Even if you use it, so you can again get back your Hanchester. Or there is a other possibility, like a simple ruthenium catalysis with a molecular hydrogen. So you can also generate this aromatase pyridine to that Hanchester. So basically what we could say, that we are not wasting that whatever the side product is forming, one can reuse it of that. So that is the way one can think about that. It is a more efficient and practical compared to in the other previous literature known approach, metal-free approach. So that the reaction is also applicable in a gram scale, but previously it works with a 7 hour. But in this case, while we are performing in a gram scale, it is required is a little longer time, around 15 hours. It was complete conversion happened. So based on this, actually, based on this protocol, we also applied to make it some kind of an different kind of an pharmaceutical based compound. In this case, if you see that the series of bioactive molecule we have synthesized using our protocol, and nevertheless the first one, there's so far not reported the antiarrhythmic log nisolipol. So we have made it first time using this approach. But other approach, the final molecule is known, but using our concept, we applied to there to have it that compound 7, 8, or 9, and so on. So basically, at the end, I should say that this protocol is very efficient and practical, because you don't have to use it any air sensitive reagent or catalysis and so on. This is all are bench stable reagent. You can do it very easily, and also it would be applicable in a gram scale. And if you could see that this is a very mild reaction condition, that was the reason we also nicely showed some very good chemoselective functional group tolerance, and nicely showed the mechanistic pathway, and where we could see that this 1,4,1,2 hydride addition happened to that quinoline moiety. And if you look at that, this is a first example where we showed that antiarrhythmic drug nisolipol, one can make it using this way. Overall, this is a very, I mean, useful. We believe that because it's operationally simple, highly efficient, environmental friendly, scalable, economical boric acid we are using. So yeah, that's all. And I obviously thank to funding agency. And at this moment, I'm just present. I have presented 2 works, but I have some other students are working some other project. So now I'm looking for if you have any question in this regard.
Thank you. Thank you very much, Dr. Das. Thank you for sharing your wonderful work with us. Now, maybe I think we can have one question. So we are it's already 11:18. So maybe we can take one question, and then if anybody has any doubts there, you can like simply email them. I think Dr. Das would be happy to answer you back. But yeah, we'll take one question.
Yeah, thank you, Professor Animesh. This is Dr. Bhaktadas from Pondicherry Central University. I just want to have one small clarification from you. And yes, when you are doing that cyanation, is it possible to do the cyanation directly from the quinoline molecule instead of N oxide?
Can you tell me, sir, once again? I cannot hear properly.
Yeah, instead of doing cyanation with the N oxide molecule, is it possible to do directly from quinoline molecule itself?
For that, using our protocol, there was no conversion.
Okay, but there are reports for the pyrrole and indoles. No, there are. I mean, directly they can do cyanation.
Yes, pyrrole and indole. Yes, right, sir. Pyrrole and indole, it is there, but in this case, there is a literature. One literature I already showed it. There, people use like a triplylic anhydride. So basically, you need some really activating agent. TMS cyanide is not enough to activate this quinoline itself. So once people use the triplet anhydride, there is a selectivity, regioselectivity issues came up in the picture. So basically C2 and C4, they are getting a mixture of compound using the triplet anhydride base and solvent.
Okay,
But
the
direct
potassium.
AMS cyanide, there is a no conversion.
Okay, the potassium ferrocyanide, did you try this for cyanide?
Yeah, there was also no conversion.
Okay, okay.
We also mention in that paper.
And when we are using that bipyridine, have we ever tried for getting that dicyano product?
Yeah, we also expect that, but unfortunately we have not observed.
But if you use excess of that cyanating reagent,
Yes, we have also checked it, sir. But we have only observed this one, but we have not observed that one. Even we have started with a bis bipyridine N-oxide, basically, and there is also selectively only one side is functionalized, other side is free.
Okay, okay.
Free means other side still N-oxide is there, even with excess.
Okay. The second part of your chemistry, you showed the reduction. When you are using the ancestor in your molecule, other than your aromatic double bonds, if any other functional groups like olefin, will it do the reduction both the sides?
No, olefin is intact. I already showed that.
Okay, okay.
Olefin, alkyne, those are intact. That is a very mild condition actually. Even if you use it BHP in other reducing agent, those are, reduced easily.
Okay. Thank you so much.
Yes, thank you.
Thank you very much, Dr. Das, for the wonderful presentation. So, yeah, anybody, if you have questions, as I told you, you can actually approach any of the speakers. They're all wonderful. I think they'll be happy to answer your queries. Okay. So, so it's 11:20. So we'll move on to the next speaker. I think we have Dr. Lenin online. So Dr. Lenin.
Yeah, Naveen, can you hear me?
Yes.
Yeah,
Yes,
I rectified the problem.
Okay.
I'm going to upload it.
Okay. Yeah. So we have Dr. Lenin as our the fourth speaker. So he's coming from Department of Chemistry, Central University of Gujarat, Gandhinagar. He obtained his MSc, MPhil, and PhDs from School of Chemistry, University of Hyderabad, under the mentorship of Professor D. Basavaya. He has postdoc experience at Technion, Israel Institute of Technology, and where he worked with Professor Maurice Eisen. And then he has several years of industrial experience also under his belt. And then he has over 20 plus publications. And his research interests are synthetic organic chemistry, synthesis of bioactive molecules, and organo and nanocatalysis. Today, I think he'll be talking about novel methodologies for the synthesis of carboxylic and heterocyclic molecules using Biles-Hillman adducts. So it's over to you, Dr. Lenin.
Yeah, Naveen, it is uploading. It came?
Not yet, I think. We don't see. Okay, yeah, it's coming.
It's coming.
Okay, let's see.
So actually, I was on in both cases. One is in the mobile, other one is in the laptop. Because in the mobile, it did not work. No, laptop. Now I was in laptop only. It is working now. Can you see my PPT, the first page?
Yes. Yeah, I think
can I go ahead?
Start. Yes. Yeah. Thank you. So it's over to you now.
Yeah. Yeah. Introduce you want. Yeah. Can I go ahead, Naveen?
Yes, please.
Naveen, can I go ahead?
Yes, please. You can go ahead.
First of all, I would like to thank my friend Dr. Naveen Kulkarni for inviting me for this talk, and also I am thankful to Professor Padmanabhan sir, senior professor in Amrita Vishwapeetham, and HOD madam Mangalam madam, and also the principal Professor Nandakumar sir for accepting me for this lecture. So I'm going to talk about the simple methodologies for the synthesis of carbocyclic and heterocyclic molecules using the Biles-Hillman adduct. Actually, this is the few slides for the students' purpose. There are so many carbon-carbon bond-forming reactions are known in the literature. in that aldol reaction, Claisen reaction, Grignard reaction, Dildal reaction, Fitting, Heck, Suzuki, and so on. In that,
I think Lenin, your speaker is muted. So can you turn it on?
yeah.
Okay.
Now it's okay?
Yes.
Actually, the Bell-Swan reaction is a carbon-carbon bond forming reaction between an activated alkene and electrophile in the presence of catalyst or catalytic system. Generally, it's a three-component and atom economic reaction. Actually, it was the first patented by A.B. Baylis and Emil Hillman in 1972. The German patent and the US patent and the same year in 1972. It is not again problem. Hello, Naveen?
Yes, I think we can see you. No problem. You can.
Yeah. Next slide. It is not moving. 1 minute. Why it is so? Next slide. It's not moving. Why it is not moving? In which slide you are?
Okay. Now it's Biles-Hillman reaction.
Yeah. The next slide it is not moving. That's what.
I think I can move the slides, so you can just tell me what to do. Okay. Once you're done, tell me. I'll move it. Okay. I'll move the.
Yeah. To the next slide. Yeah. Now, actually, in this reaction, there are several activated alkenes like acrylonitrile or MVK or methyl acrylate, ethyl acrylate, and so on, working very well. And also the cyclic activated alkenes like cyclohexene, cyclopentane, and so on. Next, Naveen. Why it is not working? Next.
That's okay.
And also there are several electrophiles like aldehyde is the most commonly used electrophiles, and also so many electrophiles which I have shown in this slide also working on this inspiring reaction. Next. Why my slide? Yeah. Coming to the catalyst part, generally the tertiary amine is the most commonly used catalyst. In the DAPCO will be the more promising catalyst. Here I have shown so many catalysts like QD or 3HQ or imidazole or DBU, DMAP, TMG, and so on. So many amine catalysts are working on this inspired reaction, and also non-amine catalysts like TCl4 and TSL4 combination in various non-amine catalysts also working on this reaction to apply in the multifunctional molecule that is called as Bilsman adductor. Next. It is medicine. Yeah, I would like to show in this slide the mechanism of the Bilsman reaction. Generally, the reaction will go through the activated alkene with DAPCO, and further it will form an intermediate jitter ion A, and further it will attack onto the aldehyde and it will form another jitter ion B. Then further hydrogen migration, it will give the Bilsman adduct. On the other hand, the pathway, sometimes MVK itself will act as a electrophile and it will form a dimer molecule. This is the most probably accepted mechanism for this reaction. Next, Naveen. Why my PowerPoint is? Next, Naveen.
Yes, I think it is stuck. I'm trying to move. Okay. Yeah, I think now I can do it. Okay.
Actually, using this Bilsman adducts, there are so many applications were known on the literature. In this literature, here I have shown some of the important molecules. These all are carbocyclic and heterocyclic molecules. It was already well established in the literature. Next, Naveen. Naveen. Yeah. And also using this Boltzmann adducts, there are several natural products and biological important molecules were also known, and these molecules like so many nucleic triol and ferritin and so many natural products and biologically important molecules was also well documented in the literature. Next, Naveen. Yeah, actually, these are the molecules I have shown. Some of the important molecules we have prepared. These all are some of the oxygen containing heterocyclic, nitrogen containing heterocyclic, and carbocyclic. These are a few examples we have developed in our research group recently for the synthesis of various carbocyclic and heterocyclic molecules. Next, Naveen. Yeah, here I would like to present the preparation of this indinone molecule using this Boltzmann alcohol, Boltzmann estates. That is actually this indinone molecule, indinone moiety is very important in the so many biological activity it is showing. For example, it's a estrogen receptor binding agent and also cyclooxygenase 2 inhibitor and potent reversible inhibitor of 3CP, and also it's a PPARY is a drug for type 2 disease. This moiety is very important. That's what we felt we want to prepare a simple methodology preparation of this indinone moiety using this Boltzmann adducts. Next, Naveen. And another one more moiety, that is piperidine moiety. This moiety is also very important because we have found so many natural products and biological important molecules like alonimide. It's a sedative and hypnotic activity, and thalidomide is a drug to prevent the sickness of the pregnant women, and so on. So septimidone, migrachatin, lactimidomycin, these kind of medicinal and biological important molecules all contain this piperidine moieties. That's what we have synthesized this kind of two moieties using the Boltzmann adducts. Next slide. So I'm going to present about these two molecules. One is indinone, another one is piperidine. How we are synthesized using the Boltzmann adducts. Here, actually, we have prepared the first the mono alkylated. We use the benzyl cyanide into the Boltzmann estate, which is 3-acetoxy, 2-methylene, 3-aryl propionate. The Boltzmann estate we are used for the preparation of mono alkylated adduct through the benzyl cyanide. This benzyl cyanide can further convert into the piperidine moiety. Another one is indinone moiety. So this is the basic idea choosing this Boltzmann estate, and the intermediate was the mono alkylated product on the benzyl cyanide. Next, Naveen. Naveen, next. Yeah. Actually, in this, first we have selected the 3-acetoxy, 2-methylene, 3-phenyl propionate, the Boltzmann estate in the presence of tetrabutanoxide base in THF at room temperature for 10 hours with benzyl cyanide. Is given mono alkylated product into 72%. So this mono alkylated product we want to synthesize the tetralone moiety, which is not forming, because on the other hand it is forming the indinone derivative. The TFA and TFFA combination in DC at reflex temperature, it is forming 38%. Actually, the formation of tetralone moiety is easy than the indinone moiety, because the tetralone moiety was 6-member ring and the indinone moiety is 5-member ring. If it is want to form, it has to isolate it. Actually, this results is very surprising to us, and then we want to investigate why the tetralone moiety is not forming, why the indinone molecule is forming. Then next, Naveen. Yeah, in this actually we have to know the methodology, to know the generality of this reaction. We prepared several mono alkylated Boltzmann adducts with benzyl cyanide, in 72 to 82%, 72 to 83%, and these monoalkylated adducts was further treated with TFA and TFFA in DCE reflex for 5 hours. We obtained the indinone molecules in 38 to 40%. Of course, the yields was not that much encouraged. Even we are want to investigate the formation of this indinone moiety. Then further we have tried next, Naveen, with other Welshman acetate, which was same acetate which was treated with the sodium borohydride in tertiary butanol at room temperature for 1 hour. We will get the rearranged adduct in 80 to 85%. This molecule was further treated with TFA and TFFA, same combination, and we obtained the yields of the indinone molecules only 18 to 20%. Then if you compare with the previous case, it was around 40%. Now in this case, it's around 20%. Still, we are more interested to know about this reaction, how it is going on. Then we further tried for other reactions. Naveen, next. Yeah, here you can see clearly, we can observe it. In case of first case, the indinone moiety at position 2, it has only contained the methyl group. Then it has given 18% and 20% yields. And the other second case, the second position, it contains one phenyl bulky group and it has given 38 and Naveen came to the first slide. Naveen, then Naveen, can you hear me?
Yes. Yeah.
Just came to the second slide.
Okay. No, I'm going now. Okay. Which slide I have to go? Number 20?
This, yeah. Why this one is not?
No, that's okay. I think somebody's. So I'll stop it here.
Go on. I will tell you. Go on. Next. No. Before that slide. Go before. Before this one. Yes, this one. Yeah, here we can see in the first case, the second position, it contains only the methyl group and it has given 18 to 20% yield. If we is there any, if there is a bulky group of phenyl group, in that case, the second case, the indinones are given 38 to 40%. Then we felt if we increase the bulkiness again with another phenyl group, that is in the third case, definitely we'll get the more yields. So for that, we want to we tried with diphenyl acetonitrile the monoalkylation on this Welshman acetate. Next, Naveen. Next. Yeah, here you see in this case the same Welshman acetate 3-hexaxy 2-methylene 3-aryl propionate was treated with diphenyl acetonitrile in the presence of sodium hydroxide and drytoluene at reflex temperature 1 hour. We obtained the desired monoalkylated diphenyl acetonitrile product. So this monoalkylated diphenyl acetonitrile was treated with the same reagent condition, that is trifluoroacetic acid and trifluoroacetic anhydride, and we got the indinone moiety, indinone molecule with 66%. So whatever we expected, we increased the bulkiness of the phenyl group at beta position and we increased the yield. And the tetralone moiety, which was not observed in this reaction case also. Then Naveen, go next. So to know the generality of this reaction, we prepared variety of a library of monoalkylated diphenyl acetonitrile intermediate with diphenyl acetonitrile with 3-hexaxy 2-methylene 3-aryl propionate, and we obtained 75 to 80% in yield. So the same the intermediate was treated with the same reaction reagent condition TFA and TFFA in DCE and reflex temperature at 5 hours. We prepared a library of compound with 60 to 80% the expected indinone moieties. the Baylisman estate was prepared from the respective Baylisman alcohol in presence of acetyl chloride in presence of pyridine, and the Baylisman alcohols was obtained from various benzaldehyde and tetrabutyl acrylate in presence of DAPCO. Next, Naveen. Yeah, this reaction, we have proposed a reaction mechanism. Actually, here, this is not the isomerization, it's through the reorganization. In this case, we have proposed the trifluorostructured anion is adding onto the double bond in aldol fashion, and it is forming a ketene intermediate. This ketene further intermediate, this ketene was through the field of alkylation and elimination of trifluoroesteric anhydride, it is forming the indinone molecule. This is what we propose the reaction mechanism. I have shown in this slide. Next, Naveen. Then the same intermediate, what we obtained the with Boltzmann estates with benzyl cyanide and triphenyl estonitrile. These two intermediates we want to further convert into the another moiety, which is what I have shown the medicinal important, which I have already discussed in the previous slides. That is piperidine 2,6-dienamide. In case of in the presence of in case of trifluoroesteric anhydride and methyl sulfonic acid in DC at reflex temperature for 4 hours, this intermediate, both of the intermediate is forming the piperidine 2,6-diene derivatives. In the first case, at the fourth position, 1-phenyl. In the second case, there is a diphenyls. These are also very good yields. They were formed around the first case 70 to 70%, other one up to 86% yield. We have obtained the piperidine 2,6-diene molecules. Next, Naveen. This one also we have proposed a reaction mechanism, how this reaction is taking place. In this case also, there will be a trifluoroesteric anhydride was forming and in presence of methyl sulfonic acid, the nitrile group is forming amide and the cyclization is taking place and the piperidine 2,6-diene is forming. Next, Naveen. Yeah, actually all these compounds we were characterized and confirmed by IR, NMR, carbon NMR, hydrogen NMR, and LCMS analysis, and also few of the molecule was further confirmed by the single crystal X-ray data. The atom diagrams of the respective molecules were shown in this slide. Next, Naveen. After preparation of this indinone and piperidine 2,6-diene derivatives using the 3-hexoxy-2-methylene 3-aryl propionate, that is Boltzmann estates. Then we felt it another Boltzmann adducts, that is 3-hydroxy-2-methylene alkane nitriles. The Boltzmann alcohol, which I have shown in this retrosynthetic strategy, can also form a piperidine 2,6-diene derivatives through Janssen-Claes treatment and the partial hydrolysis followed by cyclization and the isomerization, which I have shown in this one. So we want to use in this preparation of this piperidine diene derivatives, starting from the Boltzmann alcohols, that is 3-hydroxy-2-methylene alkane nitrile. But in the previous case, for the preparation of piperidine 2,6-diene derivatives, we have used 3-hexoxy-2-methylene 3-aryl propionate. Next, Naveen. Actually, in this case, we have studied the, there is an interesting point in this one, because the intermediate 1A, the Janssen-Claes rearrangement product, it was obtained from Boltzmann alcohol, nitrile alcohol through in presence of triethyl alcohol estate, a small amount of catalytic amount of acetic acid through the Janssen-Claes rearrangement. Actually, the product was 100%, it will be Z. It is already confirmed by NMR, and also it was published in another paper in 1980s by Professor Basvaya. And this intermediate, in case of FeCl3 and acetic acid, we treated with this reagent system and it was forming the piperidine 2,6-diene derivatives. Actually, here I have shown some standardization. Actually, the intermediate it was Z, but the final product was E. actually the amount of FeCl3 and the Ez ratios which I have shown here, the best condition was the what I have shown here. In presence of this FeCl3 and 10 hours 5 millimole 5 millimole of FeCl3 at 10 hours reflex temperature, we got the complete 100% piperidine 2,6-diene derivatives. And if you reduce from 1 millimole to 3,235, we have seen, and according to the time also we have monitored the Ez ratios of the piperidine 2,6-diene derivative. The best condition, the 100% E selectivity was obtained when we used the 5 millimole FeCl3 at 10 hours reflex temperature. There is no Z isomer was forming, and this is what 100% piperidine 2,6-diene derivative in E selectivity is forming. In this reaction, the interesting point is the intermediate was Z, but after while it is working at reaction time and the sufficient catalytic reagent system, when we use FeCl3, the Z isomer was converting into the E isomer. This will be the interesting point, and then we want to see the how the further another examples will work for this preference. Naveen? Yeah, here you see, actually the Belisiman alcohol which I have told, 3-hydroxy 2-methylene alkane nitrile, through the Janssen-Klein arrangement, it will give the Z isomer. This Z isomer will form the in presence of FeCl3 in 5 equivalents at 10 hours reflex temperature. It will form the piperidine 2,6-diene derivative. In case of triethyl orthoacetate, there will be R1 will be hydrogen. If you increase the triethyl orthopropanate, then R1 will be a methyl. In case of the fourth position, it will contain the methyl group. So this both the two varieties of the piperidine 2,6-diene derivatives was prepared using this methodology, and the required Belisiman alcohols, what I have known, this 3-hydroxy 3-methylene alkane nitrile molecules was obtained with various aldehydes and acrylonitrile in the presence of DAPCO, which I have shown in the bottom slide, in the bottom of this slide, reactions. I have shown the equation in the bottom of the slide. Naveen, next. So these all library of compounds prepared this kind of moiety, this kind of piperidine 2,6-diene molecules using the Belisiman alcohols, and this molecule all also confirmed by IR, hydrogen NMR, carbon NMR, LCMS, and CH analysis, and few of the compounds was further confirmed by the X-ray data. The R-type diagrams of 2 compounds I have shown in this slide. Next, Naveen. Actually, we want to investigate the why the Z isomer, how it is converting or how it will is forming. For this, we have studied a small reaction. In this case, we have isolated the Janssen-Klein arrangement. In the first step, the Belisiman alcohol and triethyl orthoacetate. Then we obtained the Janssen-Klein range product, which was completely Z. This was treated with sulfuric acid at room temperature 4 hours, and we were isolated the Z imide, that is 2A. So this Z imide 2A was treated with sodium hydroxide, and we obtained the Z imide. So this Z imide, the 2,6-diene derivative in Z isomer. This Z isomer was treated with FeCl3 and acetic acid at reflux, same reaction condition. Then this Z piperidine 2,6-diene derivative imide was converted into E piperidine 2,6-diene derivative. On the other hand, the amide 2A was also treated with the same reagent system, and it was also formed the E piperidine 2,6-diene derivatives. Then next, Naveen. Naveen, next. Yeah, here we are proposed the reaction mechanism. Here you see the 1A Z is the isomer, 1A of the isomer is Z. It was treated with FeCl3. There is 2 paths, one in the pathway and path 2. In pathway, the acetate ion may attack onto the double bond in 1,4 fashion. Here the FeCl3 Fe plus 3 ion will coordinate with the nitrogen of the nitrile, and the carbon will be more electrophilic. Then there is the double bond migration, and then the anti-elimination followed by the anti-elimination. Then another state ion will add onto the nitrile, and further it will form the for cyclization. On the other way, on the other side, in path 2, the state ion maybe first may add onto the carbon of the nitrile ion. Of course, here also FeCl3 plus will coordinate with the nitrogen and make more carbon more electrophilic. Then afterwards, the state ion onto the 1,4 fashion it will attack, and further cyclization will take place, and at the end we'll get the E isomer. So here the only the difference is the state ion maybe first will attack onto 1,2 fashion, or maybe first will attack onto the 1,4 fashion. 1,4 fashion, if it attacks first, then followed by 1,2 fashion, it will attack. In the other side, part 2, if it attacks in 1,2 fashion, then afterwards it will be 1,4 fashion. This is what we proposed, and the state ion, once it is attacking onto that one, then further cyclization will take place, and we got the pipette intrinsic diene moiety in Z stereo selectivity. Next, Naveen. Naveen, next.
Yes, Lenin, I'm trying. I think it's stuck.
Again, it was.
See if you can move it.
Yeah, it's not moving in my computer. Why it was happening? I didn't. It is not something.
Okay, now I think move it. We can move it. Where is it?
Again, I need to play. I need to share it.
Yes, I think you have to share it again.
Yeah.
Okay, share it again.
Very few sites are there. Yeah, it's
You share it again. We don't see your screen.
yeah, I shared. Yes.
I think maybe you can close this one, the video, and then try to upload your slides from the same device. It might work well.
Yeah, I stopped the video.
Okay.
Camera I was stopped it. Now it's working. Now it's uploading. Yeah, Naveen, it's
Okay. Let's see.
opening now. Just very few slides are there. I will conclude it.
Yes. Yeah. No
I
problem.
won't take much time.
Okay. No problem.
Very few slides are there.
Yeah, I think it's coming now.
Almost you come back to up to 32 or 32, something like that.
Okay.
Anyhow, if it is not working also, I can explain. Anyhow, first slide is showing Naveen. Yeah. Move on.
We don't see it. Wait. I don't know. Maybe it seems network issue.
Network issue. It's gone.
We don't see it actually.
Now it is not there. I have seen the no. Shall I do it again? Again I was uploaded, Naveen. Just check.
So you close all the accounts, even this video, and then try to log in again. That might
Yeah,
work.
I already closed the video.
No, this one where we can see the other device. Close this also.
Okay. Yeah. Phone. Now it's
Okay. Yes. Now
first
we
slide
see.
came.
Now I'll move to the
Almost
slide where
30. Total 43 are there.
okay, I'll go to 30.
I think I can move now. Naveen.
Okay. So I'll stop here.
Yeah, I'm moving. Now I can able to do it. It is 11. Yes.
Okay, tell me, I'll move the slides. Can we go to next slide?
Yeah. Next I can move now. Yeah, I expected this. Next I will go for the third slide. Yeah. After the Belson alcohol, which is 3-hydroxy-methylene alkyl, we want to synthesize another double bonded derivative. Same reaction condition, that is triethyl. That is sorry, Johnson reaction followed by Fe3 reagent. So we have prepared this reagent alcohol with the Belson nitrile alcohol 20% aqueous sulfuric acid. It will be rearranged, and this rearranged alcohol treated with the same reaction condition, and we obtain the expected external double bond.
Lenin, actually we hear some echo, so I don't know. Maybe it seems it's the problem with the system. So I think maybe I'll move to the Oh, that was your last one, right?
Okay.
Yeah. Now we can hear you clearly. So
Yeah,
I don't know what was. Yeah. Okay.
Then the alcohols, reagent alcohols also applied for the same reaction condition, obtained the piperidine diene moieties in 63 to 70% yields. Then further, another moiety which contains two external double bond containing molecule, piperidine diene molecule, with using the another starting material, that is 1,4-diene, which was also obtained from the Welsman bromides as shown in the bottom of the slide. This bromides was obtained from the Belson alcohol. This Belson alcohol obtained from various methyl acrylate and various methyl. This 1,4-diene molecule was also treated with the same reaction condition, and we obtained the expected piperidine diene moiety. Next. Next, I can move it. Yeah, this molecules was also confirmed by IR, carbon NMR, LCMS, CH analysis. And also, this molecule was further confirmed by single extract data, and I have shown the art of diagram of that compound. Then, yeah, it's over. Now, actually, I would like to dedicate this lecture to my PhD supervisor as well as supervisor and modification. This is the slide. These are the notes I have shown here, and this is the photo which was sent off me in Teknion when we all at our home. And this is the my lab. Naveen, can you see?
Yes.
Yeah. This is my lab. This red color tie person was the founder vice chancellor of my university, and the other person was the present vice chancellor. These three are present working. Next, this is my supervisor, Professor Basavya. He was visiting my lab recently, and the present vice chancellor is and the remaining here and others are there. Actually, this is my research group. At present, two students, Pooja and Mayuri, working as an MSc project students, and one PhD completed. Her name was Vasanta. Viva was pending. Was submitted just before the lockdown. And also presently working students are three. One is Payal and Isha. And here next slide I will show you some of the photographs while the students are when we are working in the lab. I have shown some pictures here. This is our campus. Actually, the central Gujarat is working on two different campuses. One is sector 20 and another sector 30. We are working sector 30 campus. In this building, this is the chemistry building I have shown in the part. The ground floor, my lab. Thank you for all the participants. I think it's around 80 participants was there. All the I'm very thankful for joining me. I any other if you have.
Thank you very much, Dr. Lenin. So sorry, there was a lot of, I think, network and then technical issues, but I think so all the participants were like patient enough and kind enough to be with us all this throughout the program. So I think so. We normally say at the end of the event, we got some take-home message, but now you see here we are actually delivering everything to your home. So this delivered message is like we have a lot of things to learn in chemistry. We have a lot of things to do in chemistry, especially for the students. I hope they will take this and then try to explore the many facets of chemistry and try to learn more. Okay, with this, I think now it's time to thank everybody. So we will actually now I'll hand it over to Harish, who is a MSc student, inter-MSc student of ours, because this is conducted for the benefit of the students. So he would like to express the vote of thanks on behalf of all of us, actually. So it's over to Harish. Harish.
Hello, sir. Sir, am I audible?
Yes.
Yeah.
Hello, sir. Okay, hello all. Pleasant good morning to all. I'm here given a pleasant opportunity to deliver the vote of thanks for this online symposium titled Multifacets of Chemistry Research. So actually, it was a lengthy session. We had certain connectivity issues, but we made it through. This was our first online symposium. So we are actually expecting further more such a type of activities in the future. So without any further delay, let me go into my responsibility of paving way to the vote of thanks. So I take this opportunity to thank all the prominent speakers of this online symposium. Their talks and their presentations was impeccable. Actually, it gave way to the wider aspect of chemical research. Although it was complicated, they tried their level best in order to make it simple for us. So hereby I thank Professor A. Sakthivel sir. He's from Central University of Kerala. He took the first session. It was very interesting. And I also thank Dr. Sharma S. From University of California, Dr. Dandamudi V. Lenin, Central University of Gujarat, and Dr. Animesh Das from IIT Gujarat. And these were our prominent speakers, and actually their presentation was very short and sweet, and it was filled with content, and it was very knowledgeable. I hope everybody was inspired and motivated from this online symposium. Like people say that learning is a never-ending process. It is a like a spontaneous process, and these critical or these situations will only make or add more glory to these results. So all their talks and presentations was very well, and I hope everybody was really thrilled with this online symposium. So once again, I thank each and every one of these speakers for their time and effort in conducting this online symposium. Next, I would take this opportunity to thank Dr. Nandakumaran sir. He's a principal of Arts and Sciences, Amritavuri, and he was always there for us, and he's always our guiding light. Despite his busy schedule, he was here blessing us all with his presence. So I hereby take this moment to thank you also. Thank you, sir. I also take this opportunity to thank our mother, our head of the department, Dr. Mangalam Ramanathan. She is our pillar of support, and despite every bad moments or like critical situations such as the world is going through right now, she's there to support us and to motivate us. And thank you, ma'am. Thank you for conducting this online symposium. And I also take this opportunity to thank Dr. Padmanabhan sir and Dr. Naveen Kulkarni, who has been coordinating this event and making it a fruitful 3-hour session. So thank you, sir, for organizing this, and we also hope for more such activities in the future. Okay, last but not the least, I thank each and every faculty member of our chemistry department, as well as the students who cordially joined this meeting and made this successful one. So I thank each and every one of you for kindly participating in this. And I'm also ending this vote of thanks by praying for your health and for your safety. And these are tough times. So we'll have to be more careful, but we'll have to be vigilant, and we should not stop the learning process. So I hereby end the session by chanting Loga Samasta Sukhino Bhavantu. Thank you all. Thank you, sir.
Yeah, one moment, Harish. I think we should also thank the people who have participated to like this event. We have like many people from different places and different institutes. I can see. Thank you very much for taking your time participating into this, and thank you for supporting us. So I would say. So you can actually expect more events coming from us. So so be in touch. So then so one more thing, I think we didn't get enough time for the question and answer session, especially for Dr. Animesh Das and Dr. Lenin. But again, the forum is open, so people can simply type their messages, or you can simply email them. I think they will be happy to answer and take your questions. Okay. Mangala ma'am, you want to say something?
We forgot to thank teams. It is a great support from Brahmachari Sairam and the ICTS. So because of which we were able to conduct this meeting.
Yes, ma'am. Yes, ma'am. Yeah. So thank you one and all. So we'll chat the Loka Samasta Sukhino Bhavantu 3 times, and then we'll close the program. Thank you one and all.
Om Shanti Shanti Shanti. Om Shri Guru Bhyo Namah. Hari Om.